or I don't remember.
Okay.
So, what do you want, Alexander? So the stage is yours.
Yes, thanks a lot for the kind introduction, and I'm really happy to see you all, at least here in my monitor. It would be cool to be in Benask, but what can you do? So let me just share my screen. Zack. Whoop. So, and now we start. I hope you can see what I can see. So again, it's really a pleasure to be here, and that I'm allowed to talk to you about nonlinear photonic topological insulators, which is then also the title of my talk. I mean, usually I would do some jokes about how to arrive in Benask, but this time I can't do it. I just arrived in my office, which is yeah, straightforward. Yeah, I don't want to spend too much time on the introduction. I mean, you are all here because topology is cool, in particular when you do it using photonics. Now there are a bunch of cool papers out there. I just have a small excerpt here. Yeah, so recently there was this first realization of the Floquet TIs, and then there's photonics Z2 TIs, anomalies, Floquet topological insulators. You can have topological insulators in synthetic dimension. You can have disorder studies, and so on and so forth. And there's a bazillion cool stuff out there, which you could talk about for hours, days, and weeks. So I won't do that. Recently there is, recently there. Oh, sorry, there is something. Because there's always telling me that there are people in the waiting room. So let me just click that away. Okay, and recently there is a new upcoming topic. Now, so it's nonlinear topological photonics. I mean, most of the stuff we did before, actually all of the stuff we did before, is linear. And just recently, people realized that doing nonlinear stuff is pretty cool. Now, so there are a lot of theoretical proposals here shown on the upper left. This is just a short excerpt, of course, now, I mean, or a small excerpt about what you can do in nonlinear topological insulators. And then there were a few experimental implementations, now, like self-induced topological transitions, nonlinear coupling coefficients, bandgap solitones, the Floquet TIs. So this was nonlinear already, but in the end, they all observed linear edge state dynamics. And now the question, of course, is what happens if you really go into the nonlinear regime and look at nonlinear edge state dynamics. Now, so this is just an example how we think about it. So this is in the center, this, I will explain it in detail, is a laser-written photonic topological insulator. And if you launch light, this is just here symbolized with the red arrow, with low power into the system, you see just linear diffraction. But if you go to the nonlinear regime, that means you have high input peak power, then suddenly you have an edge state forming. You have an edge state forming at the edge of the system due to the nonlinearity. So yeah, I mean, this is just these people in the waiting room. Yeah, good. Anyway, let's continue. So this is the outline of my talk. Now, so in the beginning, I will tell you a few things about nonlinearity in waveguide arrays. Then I will talk about the nonlinear directional tuned coupler, which is the basis for our implementation. Then I will talk about nonlinearity-induced TIs, then nonlinear photonic higher order topological insulators. In the end, of course, I will draw some conclusions. So nonlinear dynamics in waveguides. This is already known for quite some time. Now. So you can use the optical Kerr effect. This is shown here in the center. So you have the normal refractive index of the waveguides, but at very high powers, you get an additional contribution, usually characterized with this term N2. I, of course, won't derive it now explicitly. Just believe me that it works like this. And then in the end, you get an effective refractive index. Now, and this nonlinear contribution, of course, is proportional to the intensity of the propagating beam. And then you have to adapt the Schrödinger equation, the discrete Schrödinger equation, which means the tight binding model. And you get an additional nonlinear term here, which describes essentially a kind of self-phase modulation. I mean, when you carefully look at this, the ANs are the propagating amplitudes in the nth waveguide. The first term is the evolution term. This is a linear detuning. It's just a kind of energy term. This is the hopping term to the neighbors. And then here you get a nonlinear change of the on-site potential. When you think about it, so this beta n and this gamma an squared, this is very similar, but this is nonlinear. I don't know exactly why my slides are jumping, but we will find out later. So this is the discrete nonlinear Schrödinger equation. Of course, this is the basis, for example, looking at solitones, now discrete solitones. The first 2D discrete solitones was observed in 2003 by the Morty-Segev group. This is just an example how to look at two-dimensional X waves, nonlinear X waves in waveguide arrays. So X waves are particular nonlinear thing that are dispersion diffraction free. You can use these nonlinear effects also to route and switch light in these waveguide arrays. This was done here. So many things you can do. And of course, now we try and take this nonlinearity in order to create these nonlinear dynamics of edge states in photonic topological insulators. So when we fabricate our samples using the femtosecond laser writing technology, so you launch high intensity femtosecond laser pulses into a transparent bulk material. So we take fused silica glass, and then there is cool chemistry going on. So in the end, we just densify the material, and in fused silica, if densified, you increase the refractive index, and then you draw, literally you draw a waveguide now with the focus of the writing objective, which is a higher refractive index. So light is confined to these waveguides, and this thing is permanent. So you have permanent refractive index increases. With this, you can realize complex geometries. Now you can write the waveguides along arbitrary paths. You can arrange them in essentially arbitrary arrangements. You have full control of coupling and detuning values, and then how you excite it. You launch light into these waveguides, and then the light does what it does in the waveguide system, and then at the end you image it on a camera. And for low power, you usually use a low power laser beam, but for high powers, because of the low nonlinearity in fused silica glass, we need femtosecond laser excitations with peak powers up to gigawatts, and also some control of the pulse chirp, because it's sometimes detrimental to what we want to see. But this is the idea. Not entirely sure why my slides are jumping. Anyway, good. So this is the point. So we launch femtosecond laser pulses into this waveguides, and then it propagates, and exactly you can change the input power. For low power, you see nonlinear evolution, and for high power, you see nonlinear evolution. Okay, so this is the basis. And now let's come to the nonlinear directional detuned coupler, which is at the heart of our implementation. So let's see what it means. You all know about the directional coupler. Now, so you have two waveguides, and then here in the center, there is some coupling region where the waveguide modes, they see each other. Now, if you launch light in one of the input guides, and the waveguides have the same refractive index. So this is just a sketch of the refractive index. Now, so this is the N naught of the material, and the waveguides, they have some slightly increased refractive index, usually 10 to the minus 3. This is their refractive index. And if they have the same index, it's called tuned. And now we launch light into one of the waveguides, and then because the waveguides see each other, part of the light hops to the second waveguide and part of the light remains in the first one. You can describe it very well. This is essentially all theory, and this is just a sketch of the intensity evolution within this region here in the center. Now you start just in the upper waveguide, and then slowly light couples into the lower waveguide, and some light remains in the first waveguide. Now, let's detune the waveguides. So let's say the lower waveguide has a higher refractive index. So they are detuned, and then you get an effective hopping that is less. So now in this situation, the length, everything is the same, spacing is the same, but now they have a different refractive index, and then light mostly remains in the excited waveguide and only partially hops into the second waveguide. Now, as seen here also in the sketch for the intensity. But now comes the trick. If you put high power, you get a phase matching due to the optical Kerr effect. Now, so the N effective can be tuned such that both waveguides have the same refractive index because you have this nonlinear contribution here. And then you get exactly the situation that we had in the beginning. The waveguides are tuned, and then most of the light, I'm sorry, I'm going bananas. I'm not sure what happens here, is a ghost. A nonlinear ghost. So, okay, and then now most of the light couples to the lower waveguide and only part of the light remains in the upper waveguide, but this is a nonlinear effect. Now, so it looks the same like in the beginning, but it's really a self-induced nonlinear effect. It happens only because you launch high power pulse. If the power would be low, then this would not happen. So it's a self-induced increased hopping. That's the idea of it. So that's the idea of this nonlinear directional coupling. Okay, and then when you look at the experiment, so this is really experimental data here. We launch light, and this is the transfer ratio. Now, so the transfer ratio, if it reaches 1, all of the light would couple to the other waveguide, and if the transfer ratio is 0, no of light would couple to the second waveguide. And then you see for low input peak power, most of the light stays in the excited waveguide. And if you increase the input peak power, indeed more and more light goes into the lower waveguide. And then, yeah, exactly. So there is a chat. And they're out. In that case, they go automatically, I guess. I have no idea. It's just strange. But maybe let me just restart this. So, okay, let's try. Good. Anyway, so now with this nonlinear directional coupler at hand, we can actually look at the nonlinear dynamics. This is what I really want to show you. So let's see. And of course, as you all know, for photonics, you need some kind of driving protocol if you have a topological insulator. So, and this is now what I want to tell you in the next slides. What's the driving protocol? It's relatively complex, so I would need some time. We have a full period consisting of 4 sub-periods. So the full period is denoted with a capital Z. That's the length of the full period. And the sub-period has the length Z/4, so they have the same length. And here we denote the waveguides. With these red lines, we have coupling between adjacent guides. Now, so you see this is the structure. So the waveguides go back and forth and up and down, and that they couple only to particular neighbors. So the coupling is denoted by the red lines. Then we have 2 sublattices. One is denoted with black circles, one is denoted with gray circles. Yeah? And then the refractive index is denoted by the size of the circles. I know it's a lot of information in this protocol. I'm sorry for that. That's why I try to take time. Yeah? So if you have a small circle, it's a low refractive index. And if you have a big circle, it's strong refractive index. Now, I mean, hopefully it's intuitive. And now let's go through the driving protocol. So in the first step of the driving protocol, you see you have the black sublattice with low refractive index and the gray sublattice with a high refractive index. And then I also denoted here. So the high refractive index is in the gray lattice. And you see the black ones are coupled to the gray refractive, the gray lattices, the gray lattice on their right. So this is the first step of the driving protocol. So now this is the second step. So the waveguides change a little bit. Now you have a high refractive index in the black sublattice, and they are coupled to the gray lattice sides above them. And the gray lattice has the lower refractive index. In the third step, the refractive index distribution remains the same, but now the hopping is between the low refractive gray circles with their right high refractive black circles. So this is the third step of the driving protocol. And the fourth step looks like this. Now, again, you have the high refractive index in the gray circles, the low refractive index in the black circles, and then they are coupled like I showed you. So this is a full driving period, and then it starts all over again. So this is what we have. This is the driving protocol. It's driven. Time reversal symmetry is broken, but yes, this is what we need, but in a particular way. So it's relatively complex. And why we need it to be complex like this, I will show you now. Let's look at the edge state movement. So let's say we launch light into this lower left waveguide here in the thing. In the linear regime, it would not really couple because these waveguides are highly detuned. They don't have the same refractive index. Most of the light would stay in the same waveguide and only part of the light would hop. However, because of the nonlinearity, as I showed you before, now most of the light would couple to the other waveguide. Because we have a nonlinear effect, we have the nonlinear detuning. So in the first step, light moves to the waveguide next to it. Now there's also hopping. Okay, then now in the second step of the driving protocol, light remains there. Now this waveguide is decoupled. It's an edge waveguide. Now in the third step, again, you would argue, I'm sorry, I have no idea what happens here. It worked before. I tried this talk several times. So this is the second step. Now the third step means that the waveguides, the edge state now couples also to the black waveguide. In the linear regime, it wouldn't, because it's detuned. But in the nonlinear regime, it would couple because you tune the waveguides again. And this is in the fourth step, and then it starts all over again. Now again, you see it's like here. So this was the situation. So indeed, you have an edge state that would move, and now the question is how to characterize it. Of course, you need some topological invariant. So it's an anomalous system. I don't have time to go into the details why it's an anomalous system. That just means that the Chern number is 0, so we need different topological invariants. So we take the winding number. What can I do? This is just what we have. And now we have to calculate the winding number. In this system, you can actually do it analytically, but you need a band structure for it. So what do? We take the local band structure because light is localized. It sees only, the waveguides where it is. So it's absolutely valid to discuss a local band structure. This is where the light is. So we assume the entire lattice to look as the region where the light is, and then we are able to calculate the winding numbers. And what I show you here on the right side is the, I don't know what happens here. On the right side is the band structure. So this is the wave number. That's the projected band structure. This is the quasi-energy. So here's a big band gap in the center of the system. This is the band of propagating states. This is the band of propagating states. And now let's do the following. We decrease the detuning between adjacent waveguides in a linear fashion. So it's related to what I told you before. Now, so the light self-induces a phase matching, and now we just do it by changing the detuning between the waveguides like this. And then we also calculate the band structure. And then you see for reduced detuning, you see these topological edge states popping up. So indeed, now if there is no detuning, even if it's non-linearly induced between the adjacent lattice sites, then these topological edge states, I have no idea. I'm sorry. I really don't know what this means. These topological edge states in the system. So now, okay, and they are characterized by the winding number. And as you can see, the winding number in this case is really 1. So this is a topological system. And in the beginning, it was 0. So you have a transition where the light propagates. You have essentially locally this band structure with a non-trivial winding number. So it's really a topological effect. Okay, so and now it doesn't move on. Okay, let's look at the experiments. You have the linear regime, so we launch light. So this is the first, we have actually 2 full periods. So it means 8 subcycles and 2 full cycles. So if we launch light in the bulk, in the linear regime, light spreads. And if we go to the nonlinear regime at high input peak power, then you see some localization, reduced spreading, solitone formation in the bulk. But what is more important is also in the second cycle. So here again, so this is the output bulk state occupation. So for low input peak power, light spreads, and then you get a localization for higher input peak power. So, but if you excite light at the edge, then in the linear regime, you see light spreads, but in the nonlinear regime, it remains at the edge, in the first and also in the second cycle. And light also goes around the corner. So in the linear regime, you see just spreading if this waveguide is excited. But if you go to the nonlinear regime, you really see how the light goes down and goes around the corner. It's exactly what you expect from the photonic topological insulator. It doesn't go up, it doesn't spread into the bulk, it goes down, and there is no back reflection. It really goes around the corner. So this is the scatter-free feature that we all expect. So this works pretty well. So this is then really a nonlinear induced photonic topological insulator with nonlinear dynamics of the edge states, because what you see happens only because things are nonlinear. Now, if the edge state would lose power, a lot of power, at some point it would start to propagate linear. So this is the idea. And then in the last minutes, I'm not sure how much time I have left. I got a bit confused.
So around 6 minutes.
Yeah, perfect. Okay, so now let's just quickly go to the higher order photonic topological insulators. You probably all know what higher order topological insulators are. So usually in the first order topological insulators means that you have, for example, a 2-dimensional system and the edge states are 1-dimensional. So the edge states have 1 dimension less than the actual system dimension. And then higher order topological insulators means that the edge states have at least 2 dimensions less than the system. For example, here in a 2-dimensional higher order topological insulator, the edge states are 0-dimensional. Now, for example, here in the third order topological, higher order topological insulator, then it's a three-dimensional system, and then you also have these corner states here, which are only zero-dimensional. So there is a lot of work going on in these higher order topological insulators. Pretty cool stuff. Question still, what about nonlinear dynamics in photonic higher order topological insulators? And yeah, here I will give some first answers on that. So we start with the Kagome lattice. So this is the Kagome lattice. You see, it's very much related to the SSH lattice in a kind of 2D feature. So this is how it looks. So this is the unit cell consisting of 3 waveguides. We have intracell bonds, the intracell hopping denoted by C1, here the red arrows, and intercell bonds, so connecting the cells with the yellow C2. And then we define the dimerization with this, and then dimerization just says, okay, so either you have stronger bond within the unit cell or you have a stronger bond between the unit cells. This is essentially the idea. And if dimerization is exactly 1/2, then all the hopping is the same. That's the idea. Okay, so now let's look. This is the detuning. Now, here is a sketch of how it looks. And then you can actually calculate a topological invariant that is called a polarization X or PX and PY. And you can actually show it just the formulas. You can actually show that for detuning larger than 0.5, the polarization is 0. So it's topologically trivial. Now, and if the dimerization is less than 0.5, you see here these isolated waveguides like in the SSH model. And then the polarization, both polarizations are 1/3, denoting the topological character of the underlying lattice. Now, so this is how you see it. So now it's trivial, you have a trivial edge. And again, if you decrease the dimerization and you reach 0.5, then it jumps to 1/3, and then you see here the isolated, topologically non-trivial edge. So, and now let's see what happens if you launch light only in these edges. So you have to look at the feature of the HOTI. So this is the band structure of the Kagome lattice. So you see 3 bands. You have a flat band here, and then you have the 2 tight binding bands here. So this is the normal band structure you know. But now I show you something else, which is this. And this is not really a band structure anymore. What does it mean? I just plot the eigenvalues for a particular dimerization. So this entire band structure I showed you is the one here in the center. Now, so I just plot the eigenvalues for a particular dimerization in this plot. And if the dimerization increases, you see this distribution of the eigenvalues. And if it decreases, then you see this distribution of the eigenvalues. Now, so these guys here are the corner states. These guys here are the edge states. Now, so for example, this one is a normal bulk state. Here, you have this type of corner state. So this is the amplitude distribution. Here you have an even more confined corner state. This would be an edge state, an extended edge state, and so on. Now, so this is how you can read this diagram. And now let's look at the localization curve. So this is now really the experiment. So we'll first look at the trivial corner. That means, yeah, the dimerization is larger or equal 0.5. And then let's look, we launch light into the waveguide. So the localization is defined like this. I mean, it's just the localization parameter, right? And in the beginning, you have heavy delocalization for low power. Of course, light spreads into the bulk. And then if you increase the power, then yeah, you move up in your eigenvalue diagram because you get a nonlinear contribution to your eigenvalues. You move up, you go through the bands. That's why the localization wiggles a little bit because you reach a band and a band gap and band gap. So you see how it breathes. And at some point, you just reach the semi-infinite band gap above the upper band. And then you have localization. It's like a solitone, a normal discrete solitone. So if you go to higher dimerization, 0.8, you see that in the beginning it starts similarly, but you get relatively quickly a strong localization. But then with increasing power, the localization remains. And the reason is that light is now trapped within one unit cell. So these are the experimental images. Light is launched here in the edge waveguide. And then for higher power, you see some breathing. You move up here, the eigenvalue diagram, reach again the band, and then move up again. So about here, you approximately reach the band again. And then you move up in the semi-infinite gap above, but still the localization can't go way beyond 0.3 because light is now trapped within the unit cell. So it's trapped in the unit cell, but not in a single waveguide. And now, in opposite to that, let's look at the topological corner. Of course, exactly the same curve happens now at 0.5 that I showed you before. But now let's look at this dimerization of 0.2. So of course, you already start with a localized state. But now if you go up by increasing the power, at some point the localization decreases because you reach the band of states. And then at some point, localization increases again because you reach the semi-infinite gap. And this is shown like here. So you have a topological edge state linearly here, but you remain a topological edge state even when you are somewhere here within the band. Everything is still localized at the edge, here and here. So the entire time you see a non-linearly localized, topologically protected edge state. That's the idea. And now you would ask why this is really nonlinear and topological. So I can actually show you. So we look at the polarization. And the idea is is as follows. The light is really localized within one unit cell. So the idea is if you launch light here, and here you get the nonlinear action, and light is localized only in one unit cell. That means light does not look outside this unit cell. You are again free to look only at the local band structure. It means you can expand your unit cell within the entire lattice and assume that all these, every second waveguide behaves exactly the same as this first one. There is no light anywhere. So this gives you a way to calculate the local band structure. And with this, you can actually calculate the polarization. Here, I just show you the px polarization. And again, still you see, even for the detuning that goes up to 1, which is almost unrealistically high, you see a polarization that remains 0 or even goes to negative values. That means it's really not positive. So it's really topologically trivial. And only for dimerizations lower than 0.5, it jumps to values above 0. So here you are in the topologically non-trivial regime. It really means even for the strong detunings, you can characterize the system with a topological quantity for dimerizations that is less than 0.5, and it's topological, and for dimerizations above 0.5 is non-topological. So it's really a nonlinear higher order or second order topological insulator. Okay, so first part of the conclusion. So we first experimentally realized a nonlinearly induced topological insulator. Now the driving protocol was with the tuning dependent topology. We used a power-induced transfer ratio of directional coupler, so it's really nonlinear evolution of the edge states. And the second conclusion is we also showed the first illustration of a nonlinear photonic second-order topological insulator. We explored the linear and nonlinear features of a second-order topological insulator and introduced nonlinearity as an additional degree of freedom in these topological insulators. This is the team. They really actually do the work, so I'm most grateful to them. And I have to be grateful to all the agencies who fund our research, and I'm also grateful to you for listening to what I just said. And sorry for the stuff with the talk. I was not entirely sure what happened here.
Don't worry. I think it was very nice in spite of this. Actually, there are quite a few questions. So in general, I mean, I will let the people speak, but as we are a bit over time, so I will read the ones that they wrote. So Anya Mettelman wrote, concerning the directional coupler, does the strong driving activate the Kerr term in both waveguides or just in the one with the high-low refractive index?
This is exactly the point. So if everything was designed such that wherever you have high power, of course, you get the Kerr effect, but it was designed such that the light arrives at the directional coupler where it is, it increases the refractive index, then light transfers to the second waveguide, but when all of the light reaches the second waveguide, in order to have high enough power to change the refractive index, the coupler is already left. The coupler is at N. So all of the high power stays in the second waveguide, and then it moves to the second waveguide. And actually this is good, because even better, if you go to the second waveguide, which is detuned, it has a higher effective index, due to the nonlinearity, the effective index difference would even increase, because you get always a positive Kerr effect.
I see. Wow. Okay, then the second question that came, I think also regarding the directional coupler, Miguel Bello was asking what happens, I guess, with the coupling as power is lost due to dissipation?
Yes, it starts to be linear. This is exactly the point. So it depends on the design. At some point, if sufficiently much power is lost, it starts to be a linear system, and then it stops to be topological.
I see. Then I think that the Alberto Muñoz de las Heras raised the hand, so maybe I will try to unmute him so that he can ask himself the question. Alberto, can you speak now?
Yes, can you hear me?
Yes.
Okay. I had a couple of questions. Okay, the first one.
Well, maybe yes.
About the first order setup. How is your protocol different, for example, from the Harper-Hofstadter model that you can find in the, for example, in the Hafezzi's setup? I mean, the one that you use to realize the edge state movement. Are you sort of implementing an artificial gauge field for photons? And is there any kind of time reversal symmetry protection?
So first of all, we have to break time reversal symmetry. That's otherwise we wouldn't see this. I'm not sure. Are you referring to the nonlinear, to the higher order topology situation, or to the first part?
No. To the first one that you showed.
Okay. To the dynamics of the nonlinear dynamics.
Yeah, exactly.
And which Hafezzi paper you're referring to?
The one of Mohamed Hafezzi's. I mean,
he has many. So
yeah. Okay. The one in which he implements the Harper-Hofstadter model and he's able to find the edge states. But
this he used a two-dimensional system, right?
Yeah.
Crows.
Yeah. But in your case, it's kind of a two-dimensional system in which your set coordinate plays the role of time, right?
Yes, exactly. So this I mean, it's a very good question, and that deserves a long discussion. The point is, if you have a static system, if you have just 10 seconds, if you have a static system, and usually Hafezzi has a static system, so Mohamed has a static system, and then the light propagates through, still the entire system doesn't show any time evolution. It's just the light in the system that shows the time evolution. Whereas in our system, there's really an evolution, there's really a driving protocol. The system is driven. So this is fundamentally different. It may look similar, but the fundamental physics is different. It's really a driven system. So, I mean, it's just a short answer, but if you want, we can discuss afterwards. No issue.
Actually, I would suggest, because also there are some other questions by Lavi Upreti in the chat and Alberto Amo, but I think in the interest of time, I think maybe you can answer. I mean, the chat, we will all read it, so we can.
Yeah, I'm sorry for being long. I was a bit.
No, I mean, you were more or less on time, but also I think maybe we should have left more time for questions, because I think it's very interesting.
I mean, you're always free to write me an email. Please write me an email.
Exactly.
I definitely respond to everything.
Yes, if you answer the questions in the chat, maybe we can all also read it. I mean, they are interesting questions also. So they will. I mean, you have a look at the chat, and then you can answer to everyone, and then we will all read it. Okay, thanks a lot, Alexander. I think it was a wonderful talk. Now is the time for Jacqueline Bloch. Can you please share yours? Okay, now we see that she will talk about nonlinearities in a driven dissipative SSH lattice. Thank you a lot for accepting the invitation, Jacqueline. The stage is yours.
Okay, so do you hear me? Yes.
Yes.
Do you see my mouse also? Perfect.
Yes.
Okay, so thank you a lot for this, for organizing this wonderful workshop. It's a pity we are not in Benasque, because this is just a fantastic place. So thank you for inviting me. So actually, since we are still at the beginning of the workshop, I had planned a very introductory introduction. So I don't know, maybe I will go quite fast through it. And so what I would like to describe is really related to the previous talk. I want to talk about nonlinear experiments, and so the interplay between topology and nonlinearity. But here we will use a driven dissipative system, so a non-Hermitian system. And so we will address this physics in the most simple system, which is like a toy model for topology, which is the SSH. And I will use a semiconductor platform, so polaritons, to create solitones and see what are the properties that we can observe, and is there something new with these solitones when you pump a system which is topological. So this is the basic introduction. I'm going to go very quickly through it. So as you know, when you have a crystal, you have a hybridization of the eigenfunction, and you form bands for your eigenstates. and you have so these bands and the shape of your eigenstates are sensitive to local perturbation like disorder. And so what is super interesting with topology and why, and this is one of the reasons why this physics has been awarded a Nobel Prize, is because you can also define, so consider these bands as a system, as a really a continuous system on which you can define global properties which are related to the integral of some quantity over the entire Brillouin zone. And you can demonstrate that these quantities are really topological invariants, they are integer, and they are extremely robust to any perturbation. And one of the success of these theories is that you can actually revisit the quantum Hall, the integer quantum Hall effect, and explain why you have this quantized plateau, which are only related to very fundamental quantities, and so which define, so for each plateau, you have a different integer for this topological invariant. So one also very interesting thing is that if you make an interface between two materials which have different topological invariant, you will create states which are located at the edge and which are extremely robust to any defect, any variation of the shape of this interface. And this robustness is really coming from this topological invariance that you have. So this is, of course, super interesting for photonics because, for example, you can imagine to build a circuit in which photons will propagate in one direction, will not be scattered into the bulk because you are in a gap, and will not be backscattered because there are no states to propagate in the backward direction. So this is a super robust optical isolator, and this is super interesting. And so this is, so here I show references that you have already seen in the previous talk. This field of topological physics has really emerged in a very efficient way in the last years. And all these works were as comment il s'appelle ça, Mike, son prénom, Alexander, sorry, reminded us these early works were done in the linear regime. And so now there is really a new field which emerged, which is to see how nonlinearity, nonlinear optics, and also eventually quantum optics is modified when you address this physics in a topological system. And so here I list some of the recent work that have been done. So, for example, a lot of things have been done in conservative systems, like what we heard before. And for example, the physics of solitones in a topological system has been addressed. Then you can go into much more nonlinear systems, so be really in the quantum regime and start to be able to really model the fractional quantum Hall effect. You can go into a kind of nonlinear system, which is the laser, but somehow you laser in a state which is the linear states that you had before lasing. So this is nonlinear, but in a different way. And then you can actually get what we call a topological laser, where you laser in a mode which propagates along the edge states. And then you start to have some work on quantum optics. So what happens when you launch into a topological system, non-classical state of light. So what I would like to address here in the present talk is what happens when you play with nonlinearity, topology, but you also have drive and dissipation. So you are looking at non-emission physics. And so what I would like to discuss is the physics of solitones in the system and how robust they are to disorder and defect. So can we see some topological robustness in the nonlinear regime? And then another question that I will try to answer is whether we can take profit of the non-hermeticity to create novel kinds of solitones, so solutions that do not exist in conservative systems. So I will again start very basically with just reminding you what is this toy model, the SSH model, how we can engineer with a polariton lattice an SSH chain, and then describe the physics of this gap solitone that we can generate. So SSH, as you know, has been first addressed when these three physicists wanted to describe the physics of a polyacetylene chain. So in a tight bending approach, you can just consider a chain of identical atoms, and then you consider two couplings, T and T prime, and you have an alternation of these two couplings. So this periodic modulation opens a gap. So if you calculate the band structure, you get a gap as soon as T is different from T prime. And then if you look at the eigenstates, which are defined as their components on the two sublattices, A and B, you see that there is a phase phi which appears and which really characterize each eigenstate. And if you integrate this phase over the Brillouin zone, you get a winding number, which is an integer, which can be either 0 or 1, depending on how you define your unit cell. So, of course, if you are in the bulk, you define your unit cell the way you want, and it doesn't, you get the same material. But if you look at a finite chain, the bulk edge correspondence tells you that if you have a winding which is 1, which means if you start with a weak link, you will get an edge state because you make an interface between a material with W equal to 1 and the air where W is 0. So if you calculate here, for example, with 20 sites, the eigenstates of such a chain, you find that if you start with a weak link, indeed you have two edge states inside the gap. So actually here you have two edge states, one on the left and the other on the right. Now, if you look in more detail at the structure of the eigenfunction for these edge states, what you see is that each of them is located only on one sublattice. The left one will be only located on the A sublattice, and the right one will be only on the B sublattice. And so actually all the physics of the SSH comes from this sublattice symmetry. And you can define a sublattice pseudospin, which is defined as the component, the relative component of the wave function that you have on the A versus the B sublattice. So we will define a pseudospin S, and this is equal to 1 for the left edge state and to -1 on the B on the right edge state. Okay, so how do we fabricate such a system? We will use semiconductor microcavities. So they are made of gallium arsenide or aluminum arsenide semiconductor. We grow very high reflectivity mirrors, which define a Fabry-Perot cavity with confined optical modes. And inside the cavity, we have a nonlinear medium, which is going to provide the nonlinearity, which is a quantum well, in which we can create electronic excitations, which are called excitones. And so we are in the so-called strong coupling regime, which means that when we create an exciton, it will stay there for a while, then emit light, which will oscillate within the cavity, be reabsorbed, re-emitted again. So at the end of the day, the eigenstates of the systems are exciton-photon mixed states, which are a linear superposition of the exciton and the photon. And so why are they interesting? Because they have mixed properties. Some properties come from the photonic components. For instance, their dissipation comes from the escape of photons through the mirrors. We will also engineer lattices by shaping the photonic part. And then the exciton part will provide nonlinearity, so Chi3 because of exciton-exciton interaction. It can provide gain, so we can have the system laze. And it can also provide a very strong response to magnetic field. So if you apply a magnetic field, you can get a Zeeman splitting, and so break time reversal symmetry with the action of a magnetic field, which can be also an interesting node. Then probing the system, we will probe actually the photonic part, which escape the cavity. And so then we can directly monitor the band structure of these polaritons. We can look at them in real space. We can measure their phase and so on. So looking at photons and using optical spectroscopy tools, we can really get access to all the physics that is inside. So then to fabricate a lattice, we will actually follow a tight banding approach. The building block will be a little micro pillar like this of a few micron size, in which light is confined vertically between the two mirrors. and laterally. So you have to imagine that the cavity is vertical, the two mirrors, then the cavity, the cavity and the other mirrors. So light is confined vertically by the mirrors and laterally by the index of refraction contrast between the semiconductor and air. And so here we look at the emission from the top, and we see as a function of space that the lowest mode has the maximum at the center. It looks like an s orbital. And then the highest, the next mode looks like a p orbitals with two lobes which are out of phase. Then if we couple two of these pillars, we will hybridize the two lowest energy mode and get bonding and anti-bonding orbitals for this two atoms molecule. And then we will also hybridize the p orbital. So it's really like a photonic molecule. And then if we go for a larger system, we then get extended states for the S band, the p bands. And if we look at the function of angle, we directly see the band that we have fabricated. So then to fabricate an SSH chain, what we need is to modulate the coupling. And so this is actually an SSH chain. What you see is that here, the distance between the two pillars is quite large. They are almost touching each other at their edge, whereas these two, they really interpenetrate each other. So this guy, the T is larger than this one. And so we perform like this, a modulation of the coupling. And now if we look at the band structure, the S band have a topological gap that you see here. So we have split the S band in two. And so you see that we have the lowest band, the upper band, and these gaps which come from the modulation of the couplings. So now we can, so we could look at the edge states. What we have done in this paper is to create a defect inside the bulk. So you see that here there is a defect in the modulation. We have a link which can be either weak or strong, but which is a cut of the defect in the periodic modulation. And that way you expect to see an edge state. So this is what we have done here. You see that here we have two weak links, two consecutive weak links. And what we see is that indeed there is an edge state in the topological gap. And if we look in real space, where the light comes from at this energy, you see that indeed we have created an interface state which is located only on one sublattice. You see that all these pillars are dark and only the one that corresponds to the sublattice where there is the edge state is bright. Okay, so just here a review of recent work that have been done on polariton with the SSH model. We have actually, our group has reported a topological laser on the edge states. You can also consider the spin degrees of freedom of photons, so the polarization, and this has been studied, and they have shown, so this group has shown the effect of spin orbit coupling on the edge state. The edge state can be completely optically defined, playing with non-resonant bumping. And then there is also a work here done in the group where the link between the SSH, the edge states in graphene has been done. So measuring actually the topological invariance of the underlying SSH model that you can get defined in your graphene states. So what I want to address here is how we can trigger solitones and look at nonlinear physics. So how do we do that? What we are going to do is to resonantly drive the system. So you have to imagine that the system is going to be described by this nonlinear Schrödinger equation, where psi is the intensity of the amplitude of your polariton field. What you see is that we include the Kerr nonlinearity here in this nonlinear term. There is here a term describing the dissipation. So this is the escape of photon because of the finite line width of your polariton mode. And then there is this term, which is a resonant drive. So it's an external light that enters the cavity with an amplitude f that we control, a phase that we control, and a wave vector that we control. And the frequency omega is also controlled. So we drive the system resonantly. So just maybe I will look at the question. I don't know. No, I cannot. Okay. So what we are going to do here is not excite the edge. We will excite the bulk. So I will stand in the middle of the chain. I will excite a dimer, so two pillars close by, with an amplitude f, a given frequency omega, which is in the center of the gap. And I will look at the emission along the chain when I scan the power up. And you can see here the total intensity in blue when we scan the power up. So what we see is that there is a first nonlinear jump. And when there is this jump, we see this profile. And then when we scan further, there is a second jump. And you see that this bright region suddenly increased by one dimer on each side. So we create a solitone, which is located on one dimer first, and then on three dimer. So we are going to be interested in these solitones and look at them in more detail. So for example, here, I report the profile of these solitones in log scale along the chain when we are above the first threshold. So you see that we have these two bright pillars, which are in the solitone, and then we have exponential tail on both sides. And what is remarkable is that the tails, they are located only on one sublattice, the A sublattice on the left and the B sublattice on the right. And if we go, and so you can define a pseudospin, which is positive for the left tail, which is negative for the right tail. And if you look at the overall pseudospin, so the solitone is bright on both sides, so it has a zero pseudospin, and then the two tails compensate so that the overall spin is zero. And then we can look at the three dimer solitones and we get the same. So here there is only one side because of the problem of a field of view. So we don't look at the, so you see also that there is a positive pseudospin there, negative there, and the overall pseudospin is zero. Okay? So what we get is actually the same as what has been discussed, for instance, in this paper in the group of Kifshar, is that similarly as in conservative system, the gap solitone that you form, they have spin polarized tails and the total spin is zero. And in this paper, there is actually a demonstration that you cannot create gap solitone with non-zero total pseudospin. So then what is specific with that? Why do we have this pseudospin? Is it related to this gap, or can we get the same when we excite the system somewhere else? So as a witness experiment, we can form the system here in the gap, which is between the S and the P bands. And this is the gap solitone that we get. And you see that here, there is light on each tail, on each pillar in the tail, and there is no spin polarization. So this is what we call a trivial solitone. And here, this is what we call a topological gap solitone because we pump the topological gap. So then what is special about that? So we see that there is this spin polarization of the tail. And, oh, sorry, I forgot that. Also, we can tune the pump within the topological gap and see what happened to the spin of the tails. And this is what we get. So here, this is in the middle of the gap. And you see that, for instance, when we lower the energy, the spin decreases and vanishes when we reach the bands. Of course, here, then we get propagating solitones, and there is no more any spin polarization of the tail. So what can we do with that? We are going to look at, and this has been addressed in this paper for conservative solitone, do we get some robustness because of this particular spin texture of the tail? And to do that, what we are going to do is instead, in addition of creating a solitone in the bulk of the lattice, we will also optically induce a defect. And to do that, we are going to pump a micropillar, but this time not resonantly, but non-resonantly. So doing that, we create carriers, excitons, which interact with the polaritone and create a local blue shift. So we will modify the on-site energy of a particular pillar and create a defect. So we calibrate this defect by pumping a single isolated pillar, which is close by, and seeing what is the blue shift we create as a function of the power. And so then we do this experiment, both pumping resonantly in the middle of the gap and creating the solitone, and then adding this defect. And what we see is that the first defect, the threshold does not change, But then we see that we modify. So here we create the defect on the B sublattice where there is the exponential tail. And what we see is that we strongly reduce the second threshold. And if we further increase the height of the defect, we reduce more and more the second threshold. If we do that on the A pillar, on the pillar where there is zero intensity of the solitone, we see no effect. So the idea is, so this is fully reproduced by simulation using a nonlinear Schrödinger equation or Rospita-Evski equation. And so what we see is that there is some robustness of the gap solitone to defect located on the A sublattice because of this spin polarization. So this robustness comes from this sublattice symmetry of the lattice, which is where this topology comes from. So if we want to reproduce really this effect, what is also interesting is that if we only include the blue shift, we don't manage to really reproduce the experimental measured blue shift, reduction of P2. We need to include something more. And this something more is some gain. Actually, we create carriers and excitons when we pump non-resonantly. And so the defect is actually a non-emission defect, which has also some imaginary parts. And that if we take this into account and calibrate carefully that, we reproduce the experimental observation. So this is something that may be an interesting knob in the toolbox, is the ability with our system to also create a non-emission defect. So now what I would like to address is something to answer the question, can we do something more than what can be done in a conservative system? And the answer is yes. So what we have here is that we can engineer the pump, and we can, in particular, play with the phase of the pump. So here, what we will do is pump the system with two neighbored pillars with two different beams, and we will introduce a phase difference between the two. So the knob that we will introduce is delta phi. So we pump the system in the middle of the gap, and we will play with the phase difference between the two pumps. And here I show you, so this is done at high power when we have a nonlinear domain of 3 dimers, and I vary the phase difference between the pumps. And what you see is that we go, if the delta phi is close to pi, we start to have solutions which are not symmetric with respect to the middle of the dimer. So we start to have some spin polarization of the nonlinear solution we get. And so if we compute the total spin, we see that indeed, we start to have solutions which have finite values of the total pseudospin. And if we look, for instance, in more detail at what happens here, so slightly above pi, this is the profile of the solitone that we get. And you see that the solitone is located only on one dimer. So the solitone is spin polarized. It's only on one pillar, on one sublattice, the B pillar. And then in the tail, it is also located only on the B pillar. So this guy really looks like a topological epistate. Actually, you can understand the physics. There is actually a phase frustration when you pump the system, and the intensity vanishes on the A pillar. So this experiment is a nonlinear experiment where somehow we cut the chain by removing the A pillar with this nonlinear interference. And that way, we have really created a nonlinear topological defect, a topological solitone, which has really the properties of a regular topological epistate. So we have created an interface optically in the middle of the chain in the back. So this is a solution which does not exist in a conservative system. And to show that in a nice way, we have created a numerical experiment. So this is a numerical experiment. It's a simulation where we create this solution in the dissipative system. So a gap solitone, which is located only on one sublattice. And then at t equals 0, we remove the drive and the dissipation. And you see that this solution disappears completely. It is not a stable solution of the conservative system. So I'm going to stop here. I don't know where I am, but probably I think I'm fine. I'm sorry if I'm too late.
Time. Just
It's okay?
Yes.
So just I want to summarize that we have created interesting solitones in this driven dissipative SSH chain, that there is some robustness because of this particular peculiar spin structure that we have on the tail. And then we can even also create new solutions which are really akin topological edge states, and they are created via the nonlinearity. So as Alexander has nicely described, there is a lot of things to do now in 2D topological insulators. So we are starting this experiment. There are available 2D lattices. So for example, graphene-like topological insulator, where we can start to play with the interplay between nonlinearity and topology. And so before finishing, I would like really to thank all our collaborators. We have a very nice collaboration with the group of Alberto Amo in Lille, with the group of Guillaume Valpuech and Dimitri Solnishkov to help us with the simulation at the Institut Pascal. We are very grateful with our colleagues who are fabricating our lattices. And I would like to acknowledge the people who are doing the experiment and working in the group in Palaiseau. And more precisely, and we are very grateful to Nicolas Pernet, who has been doing all this measurement, and he's finishing his PhD in the group. And with this, I would like to thank you for your attention.
Thank you, Jacqueline, for this very nice talk. So there are already a few questions actually from Lavi Upreti. Maybe I will try to unmute so that we can answer. I mean, ask them directly.
Yes.
Lavi, can you unmute yourself now? Yes.
Hello. Yeah. Thank you, Alessandro. So thank you so much, Jacqueline, for the nice talk. So I was just wondering, when you were showing this this polaritone state, which was the mixture of this photon and the photon and the excitonic state. So I was just wondering if the lifetime of the pulse was somewhere important, because I'm not.
Pulse.
Yeah, because I know
I'm sorry, I did not mention. I mean, it's a CW excitation.
Okay.
Everything is CW.
So and how exactly I understand that? Just not very familiar.
Yes, so we inject inside the cavity, so we shine on the cavity. So let's go maybe through this band structure. Okay, so we have the SSH. So we focus a laser, a CW laser, onto one dimer. Okay? The energy of this CW laser is here exactly, so it's tuned to be exactly here in the gap. And then in transmission, we look, for example, in real space, so along the chain, where the light comes from. And then as a function of the angle in real space, in transmission, we also, so angle is equivalent to K.
Yes.
And we look at where the light comes from. So, so this is this is just the linear characterization. And then when I go to do this experiment, I pump from the top. I look from the bottom where the light comes from, and I see that there is a lot of light coming from the two dimers that I pump. This light is at the energy of the laser. It's really the transmission from my sample, the nonlinear transmission.
Okay. I think it's clear now. So I have just one quick question. Perhaps you already touched about it. Maybe I missed it. So when you were talking about this, your last part or the main part, this nonlinearity plus dissipation plus drive. And so in that case, if I remember well, the disorder which you took to check the robustness of the edge state was non-Hermitian, but was not nonlinear. Was it nonlinear also disorder? Or
no, it's not nonlinear. It's linear. It's just I have a real part of the defect. I mean, it's nonlinear. It's a blue shift which is optically created. So I have my solitone, and then on the side, on a pillar which is in the tail, so which is in the linear regime, I change the on-site energy by this blue shift, and I create also an imaginary part. So you have to imagine that here I create also some imaginary part, which is some gain, so positive imaginary part.
Okay, so actually my main question was that if this topological insulator is induced by nonlinearity plus dissipation plus drive, then the robustness of this let's say edge state should also be seen for each of them. Like is it like robust against nonlinear disorder? Is it robust against dissipative disorder? Or is it also robust against some time dependent disorder? That was my question.
Okay.
Is it that?
I would say that it is, I mean, we did not check that, but I would say that it is probably robust against all of them, because you are playing with a region where the amplitude of the wave function is very weak. We have to check with nonlinear, I'm not so sure.
Okay,
but,
I think we have to.
Yeah, we have to check that. But the idea is really that the wave function of the solitone is very weak there, so it's somehow decoupled from what happens there.
Okay. Thank you.
Thanks, Lavi. Yeah, so there is one extra question, but I think we have to move on, Jacqueline. So maybe you can answer it via the chat. I think it's a simple question.
Okay, no problem. Thank you.
So I think then, Antoine, are you there?
Yep.
Yes. So you can share the screen.
Yes.
So Antoine Broadways will talk about how to explore topology with arrays of Rydberg atoms.
So you can see
so the talk is 25 plus 5 of questions, and I will raise 5 minutes before. I will raise my hand like this so that you know that you have 5 minutes left. Okay.
Okay. So which do you see the presenter mode or the full screen?
Yeah, but we see actually your screen, no? Because we see the next now we see it.
Okay.
Now we see it. Okay.
Thank you very much. So good morning, everyone. And first, a big thank to the organizers for the invitation. Of course, it would have been nice to be present in Benasque, but okay, I have to live with it, unfortunately. So what I'm going to discuss is maybe a platform that you may not be so familiar with in the context of topology, which is to use arrays of individual atoms coupled between them by Rydberg interactions in order to engineer some topological situations. And this is what I will try to show you during this talk. This work has been done at the Institut d'Optique, which is actually just on the other side of the road of Jacqueline's lab. So we are not leaving the Plateau de Saclay. And before I dive too much into the topic, let me just show you the team. So this is our team before the pandemic, which is the reason why no one wears masks. And since then, we haven't been able to be all together to get a new group picture. But essentially, the people who did the work are Pascal, Vincent, the two PhD students for what I'm going to report, under the guidance of Daniel, who is a postdoc, and Thierry Lahaye, who is a permanent staff member in our group. And so we received a lot of theory support, and that was absolutely critical for what I'm going to present today from Hans-Peter Büchler and his team in Stuttgart. Okay, so I don't think I need to motivate too much the fact that exploring topology is interesting. I mean, this is something that you see occurring when you want to describe the quantum Hall effect, when you want to describe topological insulators. And despite the fact people have been looking at that for quite some time now, there are still a lot of open questions. I mean, for example, when you go to the interacting case, is there a difference between bosons, fermions? What are the roles of symmetries? Precisely the role of the interactions and its interplay with the topology. So once again, I don't need to motivate that too much, but essentially, if you want to revisit those questions and try to understand them better, one fruitful approach is to build in the lab some synthetic matter over which you can experience, control the parameters, and try to explore the various aspects you are interested in. So essentially, we've already heard two platforms this morning, so photon and polaritons. We're going to hear more during the week, but the one I'm going to discuss today is the one related to atoms. So this is the outline of the talk. So essentially, I will try to give you a short introduction to the platform, which I'm aware many of you may not be familiar with. And then I will try to show you two examples of, I mean, the two only ones actually we've done so far, of implementing the SSH model, and in particular, the observation of a symmetry-protected topological phase for interacting bosons. And then I will move on and try to demonstrate how we can engineer the interactions between Rydberg atoms, which I will discuss before, in order to implement a spin-orbit coupling. Okay, so let's start with the platform. So our platform, in a nutshell, is just an ensemble of interacting atoms. So this is a snapshot. It's a fluorescence image of atoms. So essentially, each of the bright dots that you see here correspond to one and only one atom, which is trapped in what is called an optical tweezer. So it's a tightly confined dipole optical trap. It's the only thing you need to know. Essentially, the atoms have to be laser cooled before we do that. And those atoms, we can arrange them. We can place many of these tweezers in various geometries up to about 200 atoms. So those are examples of a honeycomb type of lattice, a snake containing 200 atoms. So that's the starting point we have. Ensemble of atoms arranged in space. So now the distance between the atoms is fairly large. So it means that at this micrometer length distance, the atoms do not interact. So in order to make them interact, we use a second ingredient, which is a Rydberg interaction. So Rydberg states are just highly excited state of any atoms. So it means those are states with high principal quantum number. And think about the hydrogen atom for those of you who not familiar with that. Those are just the state lying close to the auto-ionization threshold. So if you want to have a classical picture of what is a Rydberg atom, this is really this Bohr model of the electrons spiraling away from the nucleus, but with a very large radius. Very large really means very, very large on the atomic length scale, because typically the size of the Rydberg atoms for n equal 50, 100 about, is in the range of a fraction of a micrometer. So this is really a large object that we have. The consequence of having this large principal quantum number is twofold. The first thing is that the lifetime of a Rydberg state is long. Well, I mean, it's just above 100 microseconds, so it may not look very long to you, but as you will see, it's long enough. And the second thing is because there is this large separation between the plus and minus charge, it means that you have large dipole moment, and the dipole moment scale like the square of the principal quantum number. So the consequence is that you develop large dipole-dipole interaction, even for distances between the atoms, which are large, very large. So typically around n equals 60, which is what we use, two atoms separated by a distance of about 10 micrometers, so it's a longer distance, the strength of the interaction is in the megahertz range. So it means that any interaction or any dynamics induced by the interaction is going to occur on a sub-microsecond time scale, which means that this lifetime of the Rydberg, although not infinite, can be considered long enough. Okay, so that's the platform. So now the very specific type of interaction that we're going to look at here is called the resonant dipole-dipole interactions. So the atoms are initially prepared in a well-defined quantum state, whatever, in the tweezer, and they are in their ground state. What we do is that we laser excite them. The details are not important here until we reach a given Rydberg state, which is the state here 60S, but it doesn't matter for the details. It is separated from an excited state by a microwave transition around 17 gigahertz. And for everything that I'm going to discuss now, you can totally ignore the plumbing and the details of the MO physics and just think of our atoms being two states. Those are two-level atoms. Okay, so those two states are coupled by a matrix element. Therefore, you can induce microwave Rabi oscillation. So this is an example of a microwave oscillation on just one and only one atom when we drive a microwave between the S and the P state. But more importantly, from the point of view of the interactions, what we have is this exchange interaction. So you have this situation where one of the two atoms can be in state P, the other one in state S, and the interaction is going to induce a flip-flop, so a switch of the interaction, swap of the interaction between the two atoms. So the Hamiltonian describing that is the sigma plus, sigma minus spin Hamiltonian, where sigma plus and sigma minus are the polymatrices. And the strength of the interaction varies like d squared over r cubed as any dipole interactions. So we have measured that on an experiment. So this is an example of just two atoms in interactions. You place one in P, the other one in S. The atoms are separated by a large distance, typically 30 micrometers for this experiment. And you do see that in a phase opposition, they exchange as a function of time their state. And because what is plotted here is the probability that one atom is in P while the other one is in S, or vice versa. Very important for what I'm going to discuss, this interaction is anisotropic. So if you have a quantization axis with respect to which you define all the quantum numbers of the atoms and you prepare the atoms, essentially if the internuclear axis is makes an angle theta with respect to the quantization axis, the interaction will be anisotropic. So if you plot the oscillation frequency of this curve, if you wish, in angular coordinate, in polar coordinate as a function of theta, you have this nice pattern that we learned from classical ENM. It's 1 minus 3 cosine square theta. But importantly, there is a magic angle for which two atoms at nearly 55 degrees do not interact. Okay, so keep this information in mind. So it's an exchange interaction, but at the same time, it's an anisotropic interaction. So now, of course, I can always think of this exchange interaction in a totally different language. I have two interacting atoms, but let me call a P state an excitation. It's now a quasi-particle, if you wish, and I reduce the problem, or I simplify the problem of those two interacting atoms to the problem of one particle which hops from one side to another side with a strength which is say 3/2, an amplitude, a probability amplitude which is say 3/2. So I have two interacting atoms and I transform that into a single particle problem of a particle hopping from side to side. So based on this, we can implement this SSH model. So this is work that we have done already quite some time ago, and you can find more information in this paper if you wish. So I will not motivate too much the SSH model. You know that, introduced late 70s as a way to describe the electrical properties, the electronic properties of polyacetylene, and now considered as one of the simplest topological models. So people have implemented that in many different synthetic matter. We've heard actually two systems this morning, mainly in the single particle regime, although what we've seen in the two previous talks was that introducing the nonlinearities makes you out of the linear regime, which is single particle regime. So if you want to develop, to describe this SSH model, essentially SS and H did the following thing. They simplified to the extreme, assuming that you've got two sublattices, A and B, and you work in the tie binding limit and in the dimerized limit. So essentially what you say is that you have two sides strongly coupled and the other side weakly coupled. So you've got the alternance and weak and strong bonds. Okay, so a very important feature of the SSH model is the presence of an underlying symmetry, which is a sublattice symmetry. The sublattice symmetry is the fact that within a subchain, the two sides are not coupled. Two nearest sides are not coupled. And the consequence of it is the fact that the single particle spectrum is symmetric with respect to zero energy. Okay, so you all know this. This is the spectrum in case of a finite size system. So you will see the presence of the H state. So essentially, you've got two possibilities. Either you end your chain with the strong links, in which case you have this kind of energy levels. It's almost analytical. It's fully analytical. So the width of the band is set by the weak link and the gap is set by the strong link. Or you can, of course, have the opposite configuration where you end with the weak link on the edge, and you see the appearance of an H state on a bulk. And so essentially, it means that within the gap, you have the presence of two states that are degenerate and other two H states. So they are degenerate in the case of an infinitely long chain. So those are the two topological state. I mean, one is called topological, the other one is called normal. So the topological are characterized by the presence of H state. So we want to implement this feature in the lab. And so we're going to precisely implement this hopping of a single particle using this resonant exchange interaction, which is mapped onto this hopping of a particle from side to side. At the same time, what you want to do is to use and to implement the salient feature of the SSH model, which is this sublattice symmetry. So you want to make sure that you've got no interaction between sublattices. So that's precisely what you make use of this idea of having an anisotropic interaction, because you can place the two subchains in the experiment at exactly the magic angle with respect to the quantization axis, which is set by a magnetic field in the experiment, but it's not important. So in this way, you can have first the normal phase, which is the alternance of strong and weak bound, but ending on a strong bound. You have zero coupling within a subchain because precisely the two subchains are at the magic angle. And you can, by just moving one atom from one place to another place, move to the topological case. Okay, this is static, and you do not move while you do the experiment. You've got just two different realizations of the experiment. Either you experience with the normal phase or you experience with the topological phase. Okay, so let's try to show in the lab that we've implemented these salient features of the SSH model. So essentially, we're going to do the spectroscopy at a single particle level. So the way we do that is that we will apply microwaves, and we will see at which frequency we add states in the system. We add excitations in the system. So we start with all the atoms pointing in, being prepared in their ground state, if you wish, the S state. We add the microwave and we check at which excitation, at which frequency we excite the system. So this is what we obtain. This is a 2D map which features the probability of excitation of an atom located at site 1 to 14. We did the experiment with 14 sites, and as a function of the microwave frequency. So essentially what you see in light here is that you've been able, in the normal configuration, to excite the lower band. Then we cannot excite anything any longer here. This is where the gap is supposed to be. So this is the gap. And then we would, in principle, should be able to couple here, but we cannot because of symmetries of the wave function, not coupling to the microwave. But that's a bit of a detail. The thing which is important is to contrast that with the second situation, where you do end up with the weakling on the edge, which is to say you are in the topological phase. And what you do see is the appearance of strong excitation right localized at the edge. So those are the edge state that we see. And the second important thing is that these edge states are actually degenerate. So indeed, we prove that we have this sublattice symmetry, if you wish. The spectrum is symmetric with respect to 0, and the two edge states have the same energy. Now you want to show that you can break the sublattice symmetry, and the way to do that is just by moving one atom away from the magic angle, in which case you introduce a coupling between this edge state and the nearby state from one of the sublattice. And if you do that experimentally, this is what we observe. Indeed, we shift the energy of the two edge states with respect to each other. So it means that we have implemented the sublattice symmetry in the system, and that we can even control it by varying the geometry. So now the challenge is, can we implement the interaction in this system? So what we've seen in the two previous talks is how to implement that using nonlinearities. Here we're going to use the extreme nonlinearities, which is to the fact that you can view your P excitations or spin excitations, if you wish. It's a two-level system, so you can map it onto a spin 1/2 system. And essentially, those particles act as hardcore bosons. So it means that if you have already one atom which is excited in P, a nearby atom in P cannot hope, the excitation cannot hope onto the other atom because it's already excited. So there is no place to go because it's just a two-level system. So this corresponds to a very specific case of interactions between P excitation, but it's an extreme one. It's just an infinite on-site interaction. So if you wish to compare with what was said during the two previous talks, this is the ultimate nonlinearity because it's an infinite nonlinearity on-site. So how do you access this regime? Well, you use again the microwave. The microwave is a way to add one by one the excitation in the system. So you transfer some atom all in S, you transfer them in P states one by one. And so essentially what we've done is we've filled, it turns out that actually the ground state of the system of interacting hardcore bosons is obtained when you have filled halfway the bulk. So essentially, if you have no connections, no weakling, it corresponds to an ensemble of dimers, one being prepared in a symmetric state, 0, 1 plus 1, 0, if you want, or up, down, plus down, up. It turns out that, I mean, now we are in a regime where, of course, J prime, the weak link is not 0, so we have a fully correlated bulk, but it's at half filling. And so we're going to check that when we're at half filling, the bulk is half filled, the edges do feature some extra robustness. It means that now we can break the sublattice symmetry, also called chiral symmetry, and keep the degeneracy between the two edge states. So I remind you what we've seen before. So the way to break the chiral symmetry or the sublattice symmetry just to place one atom away from the magic angle. So this is what we've done here, single particle regime. That's what I've already showed you. And so now we do the very same thing, but now the bulk is already half filled. Okay, and you do the very same experiment. You apply the microwave and you try to see at which excitation, at which frequency you excite the edges. And when you do that, although you have broken the chiral symmetry or the sublattice symmetry by having moved the edge atoms away from the edge state, you do find that the degeneracy is preserved. So very clearly, the case of having one excitation in the system or many of these hardcore bosons, which do interact through these infinite on-site interaction, makes the system very different and react differently. So the many-body system is intrinsically more robust with respect to the breaking of the chiral symmetry. And so this is actually the salient feature of the symmetry-protected topological phase for interacting bosons, which turns out to be the only possible topological order that you have in 1D. And so that's something that people come up with around 2012. So on the growth picture, essentially what we have implemented, I mean, this is the classification of topological phases for interacting bosons from 0 to 3D. We've, I mean, very humbly just filled one of these this line and those boxes. So that's what we have implemented. Okay. So what I would like to discuss now in the remaining, I guess it's 5 minutes, Alejandro, that I have now, something like that. I would just to give you
actually 7 minutes, yeah.
Say that again, sorry.
7 minutes you have.
7 minutes, okay. So I will just give you an idea, hopefully, of why we can, how we can use these resonant dipole interactions to implement now a spin-orbit coupling. So the idea for implementing the spin-orbit coupling is, of course, to go beyond the 1D, but going to 2D. I mean, I don't need to motivate that either. Many people are working on that with photonic platforms, polytonic platforms. It's just that usually this is the situation that people have in mind when they think about topology in the context of quantum Hall effect, topological insulator. And quite often, this is associated to the fact that you have a topological point structure, which requires, to be possible, some kind of complex hoppings between sites. So for example, if you just take a square array in this way, what you would like to implement is a coupling, which has a phase. It's a complex hopping, because in this way, the flux around one plaquette corresponds to an effective magnetic field. And so people have tried to implement that in various systems. So I just name a few of them: cold atoms in optical lattices, superconducting circuits, so you can vary the magnetic flux locally, photons, of course. I mean, there is all the chiral coupling that people have played with. So essentially, what I will try to show you is that we can implement, using the resonant dipole interaction, a spin-orbit coupling, which at the same time also features time reversal symmetry breaking, which is what you want to have in order to implement this complex hopping. So what we're going to do is, again, to play with this resonant dipole interaction, but I'm going to make it a bit more complicated. Instead of having just two levels and make each atom a two-level system, I will look more in detail at the full internal structure, almost full internal structure. So on the gross scale, you can still think of it as just essentially two levels. Those two levels, if you use the magnetic fields and electric field, you can actually split them according to their Zeeman splitting, for example. So you've got the P3 half splits into 3 states, the S1 half splits into 2 states. And so once again, the splitting is due here to the implementation of an electric field and a magnetic field. So we're going to consider just 3 of the states out of all these manifolds: the 0 state, the plus state, and the minus state. And so now let's introduce the second atom, which has exactly the same structure, and let's look at the consequence of the resonance exchange interaction in this case. Let's look at the case where one atom is in minus, the other one is in 0. Of course, what can happen is that the dipole-dipole interaction can just swap the state of the 2 atoms. So essentially, if you write this, you see it's a complicated expression, but out of this complicated expression, you have everything. The spin-orbit coupling, as I will show you, and a regular coupling. So the first thing that can occur, which is described by some of these terms, the details are not important at this time, but essentially this is the usual exchange that I've just used for the SSH model. So essentially, you exchange the 2 states in a normal way. It looks like a 2-level system. And this interaction is totally isotropic. And if you make the magnetic field perpendicular to the field, the interaction is now totally isotropic. But what I'm going to look at, to consider, is a second thing where this exchange interaction can occur off-resonantly. So essentially, the fact that you have electric and magnetic field shift the energies here, which means that you can have this atom initially in down the other one initially in 0, which swap their state, but the first one goes from minus to 0, and the other one is sent to plus at a cost, an energy cost, which is mu. And this is described at this part in spherical coordinate of this operator. So essentially what you see here, that now there is a phase that comes into play. Okay, if you just have two atoms, it's not important, this phase, because you can always gauge it away. But here I will show you that it's important as soon as you add a third atom. But essentially, this lattice process that I've described is exactly a spin-orbit coupling, because you have one excitation minus on one of the two atoms, which moves onto a second atom, but at the same time, the atoms change its internal state. So it changes its spins, so to speak. So this is really the spin-orbit coupling. So what's the consequence of that is now you operate with three atoms. So let's try to make a triangle. Two of the atoms are in state 0. The last one is in state minus. And essentially, I have two manifolds to consider. The one where I only have one minus excitations, or the one where I have only one plus excitation. And of course, they are separated in energy by mu, the mu that I showed you before. This is this mu. So now you start from this state. And what can occur? I mean, if you want this minus to turn to atom 3, for example, you can do it directly. It's the direct hopping, this exchange, which happens with this amplitude, which has a real amplitude. But the second thing that you can do is that you can go from minus on site 1 to minus on site 3, having gone through the excitation with a plus of site 2. So it's an indirect hopping, and it's in second order perturbation theory, it's the product of those two amplitudes which now have a phase. And so at the end of the day, you have a matrix, an effective coupling, which is W squared, the square of the things, divided by the energy, times the difference of the phases. But now, this difference in phases is totally independent of the orientation. Is just set by the geometry of the triangle. So this is a phase which now I cannot gauge away. So now, if I want to look at how an atom can go from site, an excitation minus can go from site 1 to site 2 to site 3, it has two paths, and you need to add the amplitude. And so the total amplitude is essentially the path of the real amplitude, the complex amplitude due to the spin-orbit coupling, and the total amplitude is known as J13, which is the complex sum of those two numbers. Okay, and the phase here, which is the Peierls phase, is set by essentially the geometry of the triangle. So in this way, you reduce the problem to essentially the hopping of a minus excitation, having fully eliminated the plus because it's an energy cost, but the virtual hopping leads to this complex chain. So I'm nearly done, Alejandro. So essentially, I will show that to you on the experiment. So we prepare the atom in state minus, and we're going to measure as a function of time of where the minus excitation is around the triangle. And what you see is that it goes from minus to, it goes from minus to 3. So sorry, it goes from minus to 3. And then to 2, so there is an order. So essentially, this excitation jumps around the circle for a given orientation of the magnetic field. And now you can revert this. So I mean, this is just the center of mass that we've plotted here. So of course, it's an experiment, so the thing decays back to an average. The center of mass goes to 0, but still you can see this chiral motion around the circle. And more importantly, if you revert the sign of the magnetic field here, you revert the sign of the rotation. So essentially, instead of going counterclockwise, it now goes clockwise. Okay, so essentially, you go from 1 to 2 to 3, while here you are going from 1 to 3 to 2. Okay, so something which is which I'm not going to describe is the fact that now, if you place two excitation in this system, you can implement a density-dependent Peierls phase, which is actually akin to a dynamical gauge field. Or you can have an interpretation in terms of anion. But essentially, this is all I wanted to tell you. So that these platforms, which combines arrays of atoms and resonant dipole interaction, allows you to implement topological situation, which we have explored in two instances. So the SSH model and a very elementary example of a spin-orbit coupling. Of course, the kind of thing we would like to do now is to go beyond this just a demonstration with 3 atoms. And those are calculations that the group of Hans-Peter Büchler have done of just what happens on a honeycomb lattice at a single particle level. This spin-orbit coupling I just described you should allow you to observe edge currents. Okay, and of course, we are thinking about implementing the hardcore interactions to reach fractional topological insulator. So with this, I thank you very much for your attention.
Okay, thanks a lot, Antoine. Very nice talk. There are already a few questions in the chat, so I will read them to make it faster. So Alberto Amo is asking what sets the spectral width of the edge states in your system?
Yes, so yes, a very good question. So essentially, I guess that what you are asking, Alberto, is what sets the width here of the edge states, if I understood correctly. This is stupidly the power broadening of the microwave. Okay, because this is a microwave excitation, and therefore, if you drive with a large amplitude, and we do need to do that in order to have a significant signal, it broadens the line. So this is really line broadening of the spectroscopy.
Thanks. And then there are two kind of complementary questions. One by Ciara McDonnell is asking, how do you warrant only nearest neighbor interaction between sites? And then Francesco Ciccarello is asking, is there a way to implement next nearest neighbor couplings?
So that's an excellent question. And actually, I cheated a bit. Because so if I just show you the dimerization here, so I make you believe that there is a dimerization. This is not entirely true because the interaction is 1 over r cubed. So the thing which is true is the fact that this J second is indeed 0. So you do have 0 interaction between nearest site because of this magic angle. But the thing which is not true is that it's just strong, weak, strong. You do have strong, weak, but you also have this coupling between the sublattices. It turns out that, so, I mean, if you want to do a comparison, a quantitative comparison with, like, for example, the spectrum, you do need to include these extra terms. But it turns out that for the symmetry protected topological, it's no problem. You can allow extra long range hopping as long as they couple different sublattices, the A and B sublattice. But you still do not need, I mean, it's still important not to have coupling between the sublattice. So in a sense, we do not implement nearest neighbor. I mean, you do have longest next nearest neighbor interactions, which are 1/8, even less, 1/10 of the other ones.
Okay, thanks a lot, Antoine. I think that we will close here so that we have some time to make a coffee and go to the toilet and everything. So
Thank you very much.
I thank you for the presentation and on the rest of the speakers, and also to the attendees that were making questions. I think that this sets the spirit of the rest of the conference. So then we meet at 11:30 for the next session.
We're going to continue with the workshop. Welcome everyone to the second session. We have a few very interesting talks ahead. And our first speaker is Andrew Foster from University of Sheffield. Please, Andrew.
Okay, hopefully you can see the slides, yes? Yep. Okay, good morning, everyone. So yes, my name is Andrew Foster. I'm a postdoc in the group of Maurice Skolnick at the University of Sheffield in the UK. Today I'm going to present our work on creating experimental work, creating topological photonic circuit elements which contain embedded quantum emitters, more specifically semiconductor quantum dots. So just before I move on, I'd just like to give my apologies on behalf of Luke Wilson, who was unavailable at the last minute to give this talk. So I'd like to thank the organisers for allowing me to stand in and present it in his stead. So I'm going to discuss two related experimental works from our group. The first I'll briefly touch on is a spin Hall ring resonator structure, photonic crystal resonator structure. And then I'll move on to our more recent work, which is looking at Valley Hall topological devices. So for instance, looking at chiral coupling in these devices and the comparison of trivial and non-trivial modes in the same device. And I'll finish with some soon to be submitted work, so unpublished results on a chiral add drop topological filter. So first, I'm aware that the background of the audience is probably quite diverse here. So just a brief introduction to our system. So we have a semiconductor platform, which is gallium arsenide, and we contain within this a layer of embedded quantum dots, which are indium gallium arsenide. And so we use typically fully suspended nanophotonic structures. And there are many reasons for this. There's example SEMs on the right hand side here. nanobeam waveguides, photonic crystals, photonic crystal cavities. And the reason we use this is it's a compact structure with small bend radii. We can have a near unity beta factor, so this is the coupling of a quantum dot to a single optical mode. It's been demonstrated that you can have near transform limited line widths in this platform. And from a scalability perspective, we can have electrical control of quantum dots in the structure. So therefore could, for instance, change their charge state, or more pertinently for scale up, bring multiple dots into resonance using electrical control. But for the purpose of this talk, why would we consider adding or looking into topological photonic approaches to augment what we already are capable of? Well, there's several reasons again, the reasons including the potential to build complex geometries whilst maintaining a small footprint. So this is based on the idea of being able to create tight angles in waveguides, which transmission is robust against, which is often not the case for trivial standard waveguides. There's the possibility of reduced sensitivity to structural disorder, so that when we go to, for instance, high group index, so slow light, there's a possibility of having reduced localization effects. And there's also a topic I'll touch upon a number of times in my talk, intrinsic chirality to the waveguide modes, which allows you to ultimately couple different spin states of a quantum emitter in different directions.
Excuse me, we cannot hear you very well now. I think there has been a change in the quality of sound, maybe because of something with the microphone or something. Maybe you.
Okay, and if I speak up, is it any better or?
No, still like hear some background noise. Yes.
Yeah,
Okay.
it's becoming. I don't know. It was like there was like a phase transition towards worse sound. I don't know why. Maybe you can just try to move the microphone a little bit, or something like this.
I'm just using the microphone in my computer, so I don't really have the. I don't have much control over this, I'm afraid. Is it totally unusable?
Well, now it's a bit better. So, well, let's try. Go ahead.
Okay. Well, I'll try and speak up and hope that it works.
Mm-hmm.
Okay. So I should move on quite quickly then. Just to give a background as to what has already been achieved using quantum dots in topological photonics. So there's a seminal paper from Ido Wax's group and Mohammed Havesi with quantum dots chiral coupled to spin Hall waveguide. Since then, they have also demonstrated a Valley Hall structure very recently. And there was also work from the Arakawa group. For instance, this nanobeam cavity structure here. And I thought I would also show this work from the same group. This doesn't contain quantum dots. However, it was a first demonstration of slow light effects in topological waveguides. So this is potentially very interesting approach for the future. So quickly, first discuss the spin Hall work. So the idea here is that there is a pseudo spin associated with a lattice, a unit cell. So the unit cell is shown in this SEM. So it's 6 equilateral triangles forming a hexagonal unit cell. And you can either move the triangles out from the center of the unit cell or move them towards the center. And this gives, in both cases, it opens a band gap in the structure at the gamma point. But it also gives opposite sign pseudospin, and at an interface between the two, a topological edge mode therefore arises. And one particularly interesting point about these is that we can consider them, whilst we're not breaking time reversal symmetry here, so there are modes traveling in both directions, we can consider them to be unidirectional by spin selection. So this is shown in the FGTD simulations here. So this is a circularly polarized source whose the direction of propagation around this bent waveguide depends on the polarization state of the source. And so what we showed first was a ring resonator structure. So this is shown here, where the white dashed line gives the location of the interface. So we have shrunken inside and expanded on the outside unit cells. And the first thing we did is to use high power PL to demonstrate that this formed resonator modes lying within the topological bandgap. And so what you see here, this is just 3 PL taken from 3 different positions on the resonator interface. And you see here they're labeled 1, 2, and 3. And we see the same modes exist at each point, indicating that the mode is distributed around the interface. But we can also see this more clearly if we now collect emission from the position of this red circle and raster the excitation laser across the device. At each point we take a PL spectrum and we then integrate this over the bandwidth specified in the plot in the upper right. And so what we can see is that indeed there are a clear mode confined at this interface. It's also accompanied by the bright spots. This is just a measurement artifact from dots which couple immediately into free space, which is the inevitable downside of this particular technique. But the key point is the presence of the modes at the interface. However, one of the major downsides of this structure, well, okay, sorry, I just quickly mention that the Q factors of these modes are relatively low. In simulations, they should have been about 10 to the 3. Experimentally, they were more in a few hundred. This is largely because they were a rather short wavelength where we believe we have additional absorption losses. So this could be ameliorated by working at longer wavelengths, but the proof of principle still counts. However, more fundamentally, the modes themselves are intrinsically lossy because they're at the gamma point in the dispersion and therefore can couple above the light line. And so this led us to move on to consider the Valley Hall type structure, for which we looked at a few different points that I'll now discuss. And so what we're using here is a unit cell which is formed from 2 circles of differing radii. So it's a rhombic unit cell in a triangular lattice. So these are circles etched into a membrane. And if we create this, what's known as a bearded interface, we see that there are actually 2 modes in the topological bandgap. Now, because in this case, it's the valley churn number which is of interest. So the total churn number for the bands doesn't give us any modes, but if we just look at the individual valleys, the K and K prime points, we actually see that there should be one mode in the bandgap. And so what we do, we attribute the lower frequency mode to a non-trivial mode and the upper frequency mode to a trivial. And the reasoning behind this is that if we take our bearded interface shown in the left, and if we modify one of the holes at the interface, so the red hole, if we adiabatically increase the size of that, eventually we arrive at an equivalent interface, a zigzag interface. And what we see is if we look at the dispersion in each case, we see that the same lower frequency mode is always there. However, the low frequency modes there. However, the higher frequency mode disappears into the bulk bands. So this was the first indication that this is the non-trivial is the lower mode. And this is also supported by what happens if we look at the transmission through a series of bends. So this is one of the advantages of these sorts of structures, the robustness against bends. And what we see here is if we send in a broadband pulse in simulation, we see that in the non-trivial region, we have a transmission that approaches unity, whereas in the trivial region, we see that there is a very spectrally dependent transmission, and it is rarely close to unity. So experimentally, this is an SEM of our device. So you can see the topological structure waveguide in the center, and then 2 nanobeam waveguides, and they're terminated with grating couplers to allow us to get light out of the chip. And I've overlaid on top of this a PL map, which has been integrated over the non-trivial region of the waveguide dispersion, which simply shows that the mode is confined at the interface. The next thing we show is that a quantum dot can couple chirally to this mode. And so what I've shown here is a simulation which shows the Stokes S3 parameter as a function of position across this interface. So in this case, the waveguide's running up the screen. And regions of dark blue and dark red correspond to regions of near unity chirality. And so as the simulation shows here, this is where we can expect a circularly polarized emitter to emit unidirectionally. And indeed, this is what we can see experimentally. So this is low power PL of a single quantum dot, photoluminescence of a single quantum dot at the interface under the presence of an outer plane magnetic field. So the field splits the degenerate spin states into orthogonally circularly polarized states. And we see that one of these is predominantly emitted from one outcoupler and the other is predominantly from the other outcoupler. So this is the first demonstration in this case that we have the chiral behavior we expect. So next we took this waveguide and bent it into the form of a resonator. So again, show SEMs and a high resolution on the right hand side here. And now we excite at high power again at the interface. And we see this spectrum. So there are several features here. So we see two regions where there are modes. So we have lower Q modes in the trivial region and some higher Q modes in the non-trivial region. And then we also have this overlap region, which in future could be interesting because it has slow light, but for the moment is multi-mode, so is of less interest to us presently. And we can look at a single mode. This is the mode highlighted in red in this spectrum. This is the mode spectrum from all three sides of the resonator. And we see once more that it is essentially the same as all points around the resonator, indicating that it is indeed distributed as you would expect. And in terms of comparing from simulation what is expected, between the comparison between the non-trivial and trivial regions, these spectra here shows FDDT simulations of resonators of differing size. So the data shown down here is for the red trace, which is 21 unit cell side length. And we see that in the non-trivial region, we get a very nice distribution of modes, whereas these are key factors are typically an order of magnitude at least better than the modes in the trivial region, for which clearly much more scattering occurs. And finally, for this device, we then added a bus waveguide. So we take our resonator and we bring a bus waveguide into close proximity with the one vertex. And what this does is it allows us to demonstrate chiral coupling of a dot. So the dot is in the resonator, couples chirally to the resonator modes, but these modes then decay also chirally into the waveguide. So this would allow us to integrate it with an extended circuit. Ultimately, we did not show this, but ultimately the idea would be to have a Purcell enhancement of the emission using the resonator. And so what's shown on the right-hand side here is simply a low power PL of a quantum dot. So at zero magnetic field, you just have one emission line, which is seen from both outcouplers. And then under the presence of the magnetic field, we split the spin states. The seam splitting is the different spin states, and we see that predominantly they are observed from the different outcouplers. So finally, I'll just like to discuss, this is unpublished work that's soon to be submitted, which is our first demonstration of a topological add-drop filter. And therefore, beyond this, some interesting chiral behavior that we've observed in this structure. So we're using once more a Valley Hall photonic crystal. However, instead of using circles as the apertures, we're actually using triangles again. And there's a couple of reasons for this, but one is that experimentally we find this to be a more robust approach than the circles. and certainly better than the spin Hall case. And so we essentially invert the unit cell, which is formed from two triangles, to form an interface. And in this case, we have a single band that stretches across most of the topological band gap. And once more, we form a resonator. So this is just a schematic. In this case, it's a diamond-shaped resonator. And the reasons for this will become apparent in a moment. And we have simulated spectrum of the modes of this with key factors of the order of 10 to the 5. So the structure we're going to create is known as an add-drop filter. So apologies if this is very elementary, but just a basic intro to what this does. It's two parallel waveguides with a resonator structure in the center. And the idea being that you can send in broadband signal, and in the through direction, there is interference between light, which is coupled into the resonator and back again with the mode that is in the waveguide. And this gives dips in the transmission. And then there's a drop waveguide, and you get complementary peaks. This can either be from the left or the right or the left, depending on the symmetry of the resonator modes. In our case, the structure is shown schematically in the bottom left. So we have our diamond resonator. We bring two waveguides in close proximity, and the arrows indicate the direction in which light flows in this structure. And in simulation, we do indeed see that we have, in the through direction, we have these dips which correspond to the imprinting of the resonator spectrum on the throughput, and we see the drop signal, the complementary drop signal at the same frequencies, same wavelengths. Or we can see this more visually if we look at the simulated electric field, and we see on resonance with a mode, the light is coupled through the resonator, whereas off resonance, the light is predominantly coupled beyond the resonator, so without interacting. Experimentally, this is the structure shown here. So I've overlaid the SEM with these dashed lines, which indicate the interface and the resonator. We have the nanobeams and the outcouplers once more, so we can get the light out of the chip. This is just an SEM showing the a zoom in of the interface. And the first thing we do is to excite at high power to obtain the resonator spectrum. So that is shown in the bottom right here. So we see several modes. They're quite broad. This is in part because this is a loaded resonator, so the waveguide coupling is quite strong. And so this is the predominant loss mechanism. The next thing we do is we move our excitation to this outcoupler, the bottom right outcoupler, and we excite at high power. And this essentially gives us a white light, broadband light source. So we're probing the structure with the quantum dot emission. First, we look in the through direction. And what we see is we do indeed get dips, which correspond to some of the resonator modes. So this is imprinting the resonator modes on the transmission. We can then look in the corresponding drop direction and see that two of these modes show a clear signal which corresponds to the drop, to the resonator modes. And for completion, for completeness, we can also look in the what we call the wrong direction, which is where we expect light not to come out. And we do indeed see a strong suppression of the signal, which indicates that basically the light is not getting scrambled, if you like, as it passes through the device. Yeah, so another way we can again look at this more visually is to look at the integrating the PL in a bandwidth corresponding either to on resonance or off resonance. And so if we first look at the, we look where we once more, we keep exciting in this bottom out coupler, and we look on resonance, we scan our collection spot across the device, and we see that as expected, most of the light comes from the drop port, whereas off resonance, most of the light comes from the through port. There is a little bit of scatter, but not very much, which is a good indication that the device isn't heavily lossy due to scattering from above the resonator or from above the waveguides. We can also do a complementary measurement in which we fix the collection at the bottom right outcoupler, and now we raster the excitation. What we see in this case is on resonance, light is coupled through the device. You do not see light from the top left corner because this light is coupled in the opposite direction and we're not collecting from there. And whereas off resonance, we see that the light simply comes from the lower waveguide because it's decoupled from the resonator. So finally come to the chiral behavior in this structure. So if we look first just at the resonator itself, just to prove that this can support chiral coupling, this is just simulations which show for a linear dipole emission in both directions, but however for sigma plus or sigma minus, we get the unidirectional emission. Now, if we bring the two parallel waveguides next to the resonator, we actually see a quite interesting effect, which is where we now get emission from diagonally opposing output ports, and this switches when you switch the polarization state of the emitter. And so experimentally, this is what we have observed. So we have our structure once more. This structure is slightly, the separation of the waveguides and the interface is slightly larger than the previous case, and the resonator modes are at a higher Q. We have 6 modes. And now we look at a quantum dot, which hopefully you can see the gray arrow here. So it's approximately, it's just about resonance with one of the modes. And we first, at low power, we look at this under a zero magnetic field, and we can see this is the data shown here. So we have a single peak in both cases from the top left and the bottom right of the device. However, when we apply the magnetic field, we obviously, again, we split the Zeeman states and we get the two different polarizations, circular polarizations. So under 3 Tesla field, we get the same peak, so the long wavelength peak is seen in both cases. And if you flip the sign of the field, it becomes the short wavelength peak seen in both cases. And the situation is quite different then when you look at the opposing ports. So in this case, at positive field, it's the short wavelength peak that is seen in both cases, whereas in negative field, if we flip the field, we see it's the long wavelength peak. So this is essentially like a sort of a bidirectional chiral coupling from a quantum dot into this 4-port system, and it is shown that it agrees with the simulation. We also have data for coupling to the next longer wavelength mode, which also shows the same behavior, demonstrating this can potentially be a broadband effect. So with that, I'll come to my summary. Apologies if for the sound issues earlier. Hopefully that was resolved. I'd just like to thank the Engineering EPSRC Research Council for funding, Luke Wilson for projects as the project PI, and most importantly Mahmood, who's a PhD on this project, who had a very significant input into these results. And with that, thank you for your attention.
Okay, thank you, Andrew, for this very interesting talk and this nice experimental results. There is a question in the chat by Alberto Amo. I'm going to read it out loud. So he's asking, what are the input-output coupling losses with extraction waveguides, and what have you done to minimize them?
So currently, in the devices I've just discussed, I would say the input-output losses are quite poor. And this was mainly because we had yet to optimize the interface. So this is what one of my students is currently doing this. So I could, perhaps if it was possibly quite clear here. So what I've done here is I've excluded the data from above the coupler because a lot of light just comes straight up from the outcoupler. This isn't important, but you can see scatter There's a few of the interfaces. However, this I'll say, this was not an optimized device. Our current simulated results of the 90%, not for this device, for our next generation of devices. But obviously, we need to get this closer to 100% to build extended circuits.
Mm-hmm. Okay, thank you. There is a question by Paloma. I'm going to unmute you. Let me see. Okay. I think you should. Yes, Paloma, please.
Hi. Hi, thanks for the nice talk. I was wondering about these experiments. Maybe this is something you mentioned, but I missed. So the difference when you excite from the left and you excite from the right is that you're able to couple to the resonator or not, right? But what is the reason for this? Is it that the interface geometry that you choose filters the other propagation direction, the other chiral mode? Is what I mean.
Do you mean in this case, sorry? Or
I think it was a bit earlier when you initially introduced the experiment. Yes, so here at some point you showed input from the left, bottom left, and input from the bottom right. Maybe I misunderstood this.
Okay, now I think maybe I've that might be
my fault. It might have been unclear. So there shouldn't really be a difference. I mean, there is some asymmetry in our structure because the waveguides are not quite centered on the bottom or top of the resonator, which might have some small effects. But in general, it shouldn't matter which direction you couple through. But obviously that will impact on then which direction the light emitted from the top waveguide. But it shouldn't matter about whether it's left or right input.
Okay, perfect. Yeah, so then it must have been that you were speaking about the off-resonant result and I misunderstood. Okay, thank you.
Yeah.
Thank you.
Okay, so I think there are no more questions. So thank you, Andrew, again for this talk.
Thank you very much.
And our next speaker is Luis Martín Moreno from Universidad de Zaragoza. Luis, please.
Okay. So thank you, Diego, and thank you all organizers for giving me the opportunity to tell you about the work that we have been doing on what happens when you strongly couple some system with some topology with light. So actually, I am going to talk about two different works. One is on the anomalous Hall effect for polaritones in transition metal dichalcoyenides, that are some two-dimensional semiconductors, and also on the breakdown of the bulk edge correspondence when you couple an SSH chain to a cavity. So to start with the first one, the idea is that you know that when it has been realized that in the semi-classical dynamics, it's not only important the dispersion relation of some particle with wave vector, but also how this wave function changes with the wave vector. This induces some anomalous velocity that occurs when the system is accelerated. So there is some lateral motion of the particle. And this is given by the Berry curvature and the Berry connection. So in our case, we want to analyze this for polaritones. So let's start with the excitonic part. For that, we are going to consider these transition metal dichalcoyenides that are very interesting materials that are composed from one atom from this column and two from the chalcoyenide column in this configuration, that is the honeycomb configuration. And actually there is one MO, this is one particular case, this is MOS2, this one atom, molybdenum atom and two sulfur atoms in this configuration. But actually the two sulfur atoms, you can make some symmetric and antisymmetric combination, and for the exciton that I'm going to consider, only one of the combinations play a role. So this is like an effective system with two different atoms. So that is going to be characterized by something like a direct equation with a mass, because the two atoms are different. So it's like graphene with two different atoms. In bulk, this material presents an indirect gap. It's a semiconductor, but it's very interesting that in the single layer of this material, the gap becomes direct. And thus, this material shows a very strong light absorption and electroluminescence. And also, because of the 2D character, the Coulomb interactions are very weakly screened, and thus the binding energy is much larger than in a normal semiconductor. Actually, is about 10 times the room temperature, so you don't have to cool the systems to see the excitonic optical response. And also the exciton size is much smaller because of these large Coulomb interactions. So there have already been some studies looking at what is the spectrum of these excitons that are like hydrogen atoms in 2 dimensions. But of course, now there is some dependence on the underlying band structure that has this honeycomb lattice, and some, as I said, is represented by a Dirac equation. So there are some effects of this the topology associated to the Dirac equation already at the level of the energies of the excitons. So these excitons, actually, there are a number of them. I'm going to consider the one with the lowest energy. And actually, because there are 2 valleys, this honeycomb lattice has 2 valleys, and the system does not have inversion symmetry. So these 2 valleys at the K and K prime points are not equivalent. And in principle, the excitons can have different spin structures for the electron and the hole. But in the lowest energy exciton, there is due to the spin orbit interaction, there is a strong link between the valley degree of freedom and the spin structure. So actually, I don't have to consider the spin is linked to the valley. So this, of course, for different valleys, they have different configurations of spins. A very interesting property of these materials is that you can access excitons or electron hole pairs in different valleys just by illuminating light with different chiralities. So if you come with circular polarization, at right-handed circular polarization, you excite one of the valleys. If you come with the other polarization, left-handed, you excite the other valley. And this has been used, for instance, to find the valley hole effect. That is the following. You create electron and hole pairs or excitons, but under the presence of a strong electric field, these particles are going to move, and due to the Berry curvature, underlying Berry curvature, electrons are going to move in one direction, lateral direction, and holes in the other direction. So this is going to create a voltage difference, and thus a Hall effect. And this depends on the valley that you are exciting. So the sign of the voltage depends on the polarization of light that you are using to create this electron hole pairs, because they are in different valleys. It has also been shown that the excitons present this Hall effect, but for that you cannot do as before and have accelerate the exciton with an electric field, because this electric field is going to dissociate the electron and holes that move in different directions. So instead, what people have done is to enhance the temperature in one of the regions, and by diffusion, this exciton is going to move. And when it moves, it's going to pick up a lateral drift. And this drift depends on the polarization that was used to excite. So this is seen in photoluminescence of this exciton. Eventually, it's going to decay and it's going to emit light. And you can see that there is some lateral shift depending on whether you excite it with left-handed or right-handed polarization. People have also included these monolayers inside of cavities. And then they have seen this strong coupling, the splitting. This is the exciton line, this would be the cavity line, and these are the polariton that are clearly seen in the experiments. So they have achieved the strong coupling regime. So, but the fact is that actually the Berry curvature of these exciton polaritons may arise from different sources. First, the exciton has imprinted the Berry curvature of both electrons and holes. And as they saw in this experiment, the photon, if you include this in a cavity, the photon also has two polarizations, and therefore this internal degree of freedom can also provide the Berry curvature, and it does. But also in this paper, they show that even if you have two species that do not present any Berry curvature, if the coupling between them, they are coupled through this stem, if this coupling has some phase in it, some winding number in the phase, in the coupling, then you can have polaritons that have well-defined Chern numbers. So actually, the origin of the work that we did is which contribute dominates, and actually what is the Berry curvature of the exciton polariton. Okay, so for that, I'm going to drive you through the calculation. First, we need the exciton photon Hamiltonian, and we can find this from first principle. We start with the electron Hamiltonian, that as I told you is a direct Hamiltonian with mass. So these are the two valleys with the two different spin configurations, but in the lowest energy exciton, as I told you, the spin configuration is fixed. And for each valley, we have a direct Hamiltonian that can be expressed in terms of these direct matrices. And this is expressed in the spinor that now are the components of the wave function in the two atoms that compose the unit cell. So this is the direct Hamiltonian. It has the same form as for graphene, and the chirality is included in this coefficient tau that actually is the index that characterizes the valley. So you can find it's very easy to diagonalize this. You have the two energies, and actually also the eigenfunctions that are analytical is like in graphene. So from this, we can create the excitons, and for that, an exciton is a combination of a hole in a given valley in the conduction band, in the valence band, and an electron in the same valley in the conduction band. There are also intervalley excitons, but we are not going to consider those in this work. And you can minimize the energy, and you can get what is the relative weight for the different wave vectors that compose the wave packet. With this, we have the exciton Hamiltonian, that is just a kinetic energy plus the gap to create the electron-hole pair, and the binding energy, because you have this attraction between the electrons and hole that actually reduces the energy with respect to the gap. With respect to the planar cavity, this is very simple. We are going to consider a metal cavity that is planar, and actually the vector potential, you know that this can be there are two modes, the transversal electric and the transversal magnetic mode. This is with respect to the two-dimensional layer, and is important for what follows, that the transversal electric mode, of course, is contained, the electric field is fully in the 2D layer, while the transverse magnetic mode has a part that is longitudinal and has a part that is transversal. Actually, for normal incidence, both of them would be in the plane, but when the wave vector is away from the normal, then the transversal magnetic mode has a reduced weight or reduced component in the in-plane, a reduced in-plane component. And it's very easy to follow it's a textbook example to quantize this field. So we have the Hamiltonian, that is actually the Hamiltonian for a waveguide, in simple waveguide. So now, in order to compute the exciton phonon coupling, we can start by computing the electron phonon coupling. For that, we expand the Hamiltonian close to the minima, and this is simple because we had this Dirac Hamiltonian, so it's linear in the wave vector, and we do the minimal substitution, and therefore this Hamiltonian couples with the electromagnetic field just with this term, and these are derivative of the Hamiltonian with respect to k that are analytical. Okay, so this is the electromagnetic coupling with the to the electrons in the MOS2 layer. For the exciton coupling, what we have to do is to project this interaction onto the subspace that contains 0 excitons and 1 photon, and 1 exciton with a given wave vector for the center of mass and 0 photons. And for that, we expand the electron wave function in order Q squared, because you know that the photon has a very small wave vector with respect to that of the electron. So this expression is justified. And with that, we can get, after some work, the photon exciton coupling, and it has this expression that you can recognize that you can is in the rotating wave approximation, when you can annihilate one exciton and create 1 photon, and vice versa, with some coupling coefficient. I'm not going to enter into the expression for the coupling coefficient. It's sufficient to say that you can couple to both the TE and TM polarizations. And for the coupling with the TE polarization has an amplitude, and the coupling with the TM polarization has an amplitude that now depends on how of the fraction, so to speak, of the incoming wave vector that is along the normal direction. So when you are at normal incidence, or when Kz is equal to 0, this is actually, sorry, when Kz is equal to K, this is 1, and these two couplings are the same. But when the wave vector is not in the normal direction, then the coupling to the TM polarization is smaller, reflecting that there is less, that the projection into the plane for this component is smaller. So if we now change the polarization basis from this linear polarization to some circular polarization, of course, if these two components were the same, if these two coefficients were the same, then you could couple eventually to only one of these polarizations. But because they are not the same, as we saw, what happens is that for a given wave vector, the coupling to the T polarization is larger than to the TM polarization. So you have an elliptical coupling, and this can be decomposed on something that is circular plus something that is linear. So the circular part is going to couple to only one of the polarizations, but the linear part is going to couple to both of them, because the linear is like the sum of the two circular polarized polarizations. So this means that when the wave vector is not normal, excitons couple to both linear polarizations. So finally, we can create the Hamiltonian in the basis of the two excitons, one in each valley, and the two polarizations. So it's a 4x4 Hamiltonian, and it has the form. This is what we would have at if the wave vector would be normal. So you would couple only to one valley and one polarization, or the other valley and the other polarization. But the wave vector Q is different from 0. This is the normal, the in-plane component of the wave vector. When Q is 0, the wave vector is normal, and then this is 0, and this is the well-known rule for excitation of excitons with circular polarization. But when this Q is different from 0, you see that this term couples everything in the Hamiltonian. Okay, so on top of that, this contains a winding number, so it has some topology in it. So this Hamiltonian, you can create the modes, and now this is the original exciton, this is the original photon dispersion, and now we get this polariton dispersion relation. And due to this out of plane coupling, then we get some splitting, as you see at Q equals 0, when the wave vector is 0, the in-plane wave vector is 0, these modes are degenerate and they open up. But importantly for topology, what happens is that this term is going to couple everything together, and then the Chern number is going to be 0 essentially. In order to see that, notice that we have now a composite state where the polariton, this is quite general. You have a polariton that is composed with is a linear combination of some elementary constituent, but the elementary constituent has an internal structure that also depends on K. So when you compute the Berry connection or the Berry curvature of one particular mode, one particular band N, then you get two contributions, what that comes from the derivative of the coupling and what that comes from the derivative of the wave vector, of the wave function of the constituent. So you have some extrinsic contribution that comes from the coupling and some intrinsic contribution that comes from the that reflects that the constituent is already a composite particle. So as I said, because of this coupling between all terms in the Hamiltonian, and this system is time invariant and symmetric with respect to time inversion, and then everything cancels out and you have zero Berry phase. So in order to get some topology, we need to break the transversal symmetry. So we have to apply a magnetic field. And when you do that, then these two exciton bands split, and these bands split all the time. So now you have 4 different polaritons. And actually you can divide the spectrum and consider only these 2 bands and these 2 bands, the lower polaritons and the upper polaritons in isolation. And via a Schrieffer-Wolff transformation, you get an effective Hamiltonian for this upper polariton manifold and this lower polariton manifold. And actually this Hamiltonian is the same as for gap bilayer graphene. So this has been solved and there are analytical results. So these are the results finally. This is the Berry curvature as a function of wave vector for the lower polariton and the upper polariton. And as you can see, they are different because this Berry curvature depends on 2 things. First has a bell shape, so it's 0 when Q parallel is equal to 0, but it also depends on the splitting between these 2 systems. And as you see here, the splitting is smaller, so there is more Berry curvature than in that case for the lower polariton, that the splitting is larger, and this reduces the Berry curvature. And you can see the different contributions. Actually, for Q equals 0, the extrinsic Berry curvature that comes from coupling is negligible. This curve will go to 0, and we only get the extrinsic Berry curvature, but this is actually much smaller than the extrinsic one that dominates for the upper polariton. So now we can study the dynamics of the wave packet. We consider the same system as was analyzed experimentally, but for excitons, where we have a thermal gradient, the polariton is going to move, and we assume that when it moves, it's going to pick up some wave vector, and it's going to, so finally the displacement, the lateral displacement is going to be the integral of the derivative, and the derivative is related to this Berry phase. So actually it's the integral underneath these curves. And as you see, it's much larger for the upper polariton than for the lower polariton, and is dominated by the extrinsic coupling. So actually these displacements are rather large, and they are much larger than in the case of the exciton Hall effect. And it's just as a note, it's interesting because both for the exciton Hall effect and the polariton Hall effect, of course, these are lateral motions that are for neutral particles. So with this, I pass to the next topic, that is the breakdown of the bulk edge correspondence in strongly coupled systems. And here I'm going to consider a different system, is the SSH model. Because of the previous talks, I don't have to present this, so I skip it. It's just the SSH chain. And we are going to implement it with some particles that some dielectric particles that are going to have some dipolar moment. And we are going to consider these as elliptical particles to simplify. So the dipole is going to be oriented along the x direction. And we place this chain of particles that are placed at different distances. So they are going to interact between the dipolar interaction, that is short range. So this distance is going to translate different distances are going to translate into different couplings between the particles that are closer or farther apart. And on top of that, we are going to include this system in a rectangular waveguide with the condition that this is very long along the direction of the particle, of the chain of particles, and then it's going to be much larger in the y direction than in the x direction. So we adjust everything so there is only one waveguide mode playing a role in this system. All the other modes are much higher up in energy. So this is our system, and these are the uncoupled bands. So this is to show, so this in red and blue, we have the two uncoupled bands for the chain of particles. So this would be the SSH bands with the gap. This is for an infinite system or periodic with boundary conditions, whatever you prefer. And this is the photonic band, just to show that just by changing the height of the waveguide, we can change the energy of the bands, and we can make these bands getting closer and closer to the original SSH bands. Okay, and these are uncoupled chains. We are going to consider the situation when the Chern number is 1. So this is the condition where for the uncoupled for the uncoupled chain to the photonic mode, there would be some H state in the chain due to the bulk H correspondent. So this is what happens when we increase the thickness of the waveguide. So here is a zoom of this region. Okay, so we are very, very close to the SSH bands. So we are so close that we are not seeing in this representation the photonic bands, but these are now the bands for the coupled system. And as you see, for this particular width of the waveguide, the influence of the photonic band on the upper and lower bands is minimal. But now we increase this thickness, and there's a band repulsion between the photonic band and the SSH bands, and this creates a bending here that increases and increases. And I have represented 3 different critical positions. Here is, at this case, we are going to see, at this particular LX, we are going to see that the bulk H correspondence breaks down, but there is nothing special in these bands. Nothing special occurs here. At this particular point, the gap closes, but is the overall gap. So the minimum of the upper band is equal to the maximum of the lower band. And at this particular case, these 2 bands touch. So locally the gap closes. And then we see that in all these cases, the Chern number is 1, the Thak phase is pi, and in this particular case, when the bands touch, then the Chern number is, and the Thak phase is 0. Okay, so this can be done by these Chern numbers, or the Thak phases can be computed from the wave functions, but they can also be seen in doing the following. Because we have one photonic mode and 2 and 2 degrees of freedom associated to the particles, then we have a SU3 Hamiltonian, but because the photons couple to the particles and the particles to the photon, we can integrate out the photons, and we get an effective SSH Hamiltonian with now these are the Pauli matrices, and these coefficients are now depend on the coupling and depend on the distance between the bands, the photon bands, and the SSH bands. Okay, and you know that when this so now we change Q and we change these phases, and this coupling coefficient change. You have one that multiplies sigma x and another one that multiplies sigma y, and you know that in this parameter space, when going around when changing Q, you have to see how these coefficients change, and if they enclose the center, then you have some topology, and if not, the Chern number is 0. And in that case, we are not changing the properties of the particles, we are changing the properties of the photon. And what happens is that initially this ellipse picks up this shape, and here when the bands touch, then you have something that goes to 0, and from here they above the 0 with this Pac-Man shape. So again, this is a representation that shows that again, here you don't enclose the 0, and here the sac phase would be 0, and it would be 1 for the rest of the cases. Okay, so now if we do a finite system, I told you that the bulk edge correspondence breaks down. So this is because we can take now a finite waveguide with a finite number of dimers, and here we represent as a function of this width of the waveguide, we represent the participation ratio. That is this quantity that is used in many studies in localization. Essentially tells you what is the spread, how many sites the wave function is visiting. And you see that this here is around, for this chain of 100 dimers, this is of the order of 100, but here you have the state that is the edge mode that is of the order of 2, and then it changes and couples to these modes and hybridizes and loses the localized character. And this can be seen, if we do the same as a function of number of dimers in the chain, then you see that as a function of, you always have a mode that has a participation ratio of the order of 2, but importantly, it is not important that it is of the order of 2. What is important is that it does not depend on n at all. And you have something that depends linearly, that are all the rest of modes. While when you enter in this region where the bulk edge correspondence breaks, you have this coupling, and then you have this mixed state that actually increases more or less linearly with n, with a much smaller coefficient. It's not fully extended, it's a resonance, but actually it couples to the band of extended modes, and it goes linear with n. Okay, so with this I finish. I leave you here the conclusions, but I stop here. This is what I said before, and I thank you for your attention. I'm ready for questions.
Okay, thank you, Luis. Are there any questions? There is in the chat. Miguel Bello is asking, where is the breakdown? I'm not surprised that the edge state loses its localization if the topological invariant changes. What am I missing?
No. Maybe I did not explain properly. Here, in this case, see, in this region here, the Chern number is 1, but the localization is not there. So it's not localized. It's a resonance, but it's coupled to the continuum. So it's only when the Thak phase is 0, then there is there are no localized modes. But before that, you have conditions where the Chern number is 1, but you don't have localized modes. So this is the breakdown.
There is a question by Paloma who's asking, do you have long range interactions between the dipoles?
But this is not essential. Actually, we also did the calculation without long range interaction, just with the nearest neighbor interaction, and nothing changes. So it's not related to the long range interaction.
Mm-hmm. And Jacqueline Bloch is asking, can you precise what is the origin of the phase phi in the Hamiltonian?
You mean in the first part?
I guess so. Well, this is, I understand. Yes.
Yeah, I don't know whether.
Yes, I guess it's this phi.
Yeah, this comes because we are because they have the left-handed and right-handed polarization have different winding numbers, and because you are coupling one with the other, there's a change of 2 in the winding number when you go from one to the other.
Okay. Mm-hmm. Okay, there is a last question by Miguel Bello. He's asking, somehow the gap closes before the change in the topological invariant. Is this correct? Well, so he's
okay, we represented this because in the SSH model, these 3 points would appear at the same position in parameter space. So you would close the gap, you could break the bulk edge correspondence, and you would change the thug phase at precisely the same point in parameter space. Here, we obviously in the thug phase is something from the infinite system. This occurs when the bands actually touch, okay, and it occurs in this point. But actually, these 2 bands, the gap globally is close before that. But I don't think this is relevant. It's more like a curiosity, you know, because this here nothing happens to the thug phase. It's only that you don't have you would have an indirect gap that closes, but it's the direct gap, the one that changes the thug phase, the topology of the system. And here before that, then you have this breakdown that that is not related to the opening and closing of the gap. In the infinite system, clearly in the finite system, what happens is that this chain of dimers have all the bandwidth spreads farther down, and some of these modes enter into the region where the gap mode is. Sorry, so the edge mode, and they hybridize.
So Diego, I remind you that you can unmute the people. So I don't know, maybe for these discussions.
Yeah, so it's better if I,
yes,
because they are writing the questions in the chat, but I think it's better if I just unmute, right? Let me see.
Because if I
yeah,
share,
if you raise your hand, it's easier to unmute you because you appear on the list on top.
but you can also search them in the chat. But anyway, yeah, I mean that for this kind of discussions, like look, Miguel is raising the hand. I unmute him.
Yeah.
Okay, thank you. Yeah.
Hi, Luis. Thank you for the explanations. No, I was just wondering whether these delocalization of the edge modes can be due to this closing of the gap. I think for the localization properties, it doesn't matter that even though you still have an indirect gap, it's not like the gap is not fully open, even though the bands do not touch.
well, you know, it's clear that in the finite system you are right. So there's some mixing of this localized mode, some hybridization of the localized mode with some extended mode. But this is in the finite system. The bulk edge correspondence, if I understand properly, relates what happened in a finite system with what happens in an infinite system. And in the infinite system here, there is no band closing, nothing. It's only a property now that if you go to the finite system, okay, something's happened. But you cannot relate here. I could not say there is anything particular at this particular thickness for the wavelet. There is nothing special. When I see this, there is nothing special with respect to what happened with something a bit wider or thinner.
But in panel C, yes, no, because the gap closes also in the infinite system.
Exactly. In panel C, yes, but in panel C is not related to panel C would be this point. And that condition, the edge mode has already disappeared.
I see.
Okay, thank you very much.
Okay, if you, a last question by Paloma, and very last question because we are running out of time. See, Paloma, you want to ask?
Okay, so very quickly. So then what is what can be the origin of this? Can we interpret it as a non-Hermitian effect, like a skin effect, something like this?
No, it's not Hermitian, and I think it is related. We have simple models. We are now exploring simpler models where this already happens, and I think it's because you are coupling two particles, so to speak, with very different nature. So it's yeah. So it's not related to what I mean is it's not related to, for instance, long range interaction, although it may play a role, but it's not essential for this. But
yes.
it's the fact that you have two things that are not equivalent, and then this bulk edge correspondent may break down.
Okay, yes, I understand the long-range interaction part, but still, I mean, even if you're not coupling to the continuum, you're still coupling to a photon, so maybe you can understand that as non-Hermitian.
Yeah.
Thank you.
Okay, thank you, Luis. It was very interesting. So now our next speaker is Paloma Arroyo Huidrobo, who comes from the Technical Institute from Lisbon. And well, let me remind you, if you want to make questions, if you write in the chat, I will read them, but it's better if you raise your hand, because then I think I will just unmute you, and I think the communication will be more fluid with the speaker. But anyway, so now it's your turn, Paloma, please.
Okay, thank you. Thanks so much, Diego, and thank you also to the organizers for giving me this opportunity to present my work. So, sorry, let me close this. Yes. So, in this talk, I will speak about topological nanophotonics, or realization of topological photonics that rely only on lattice symmetries, and I will focus on discussing some specific aspects of photonics, which we have also seen in the previous talk, which are long-range effects and radiative and retardation effects. So, as you know, and we have seen many examples already this morning, there are a wide range of platforms that are available to realize topological photonics, including photonic crystals, arrays of waveguides, arrays of resonators, microcavities, and so on. But in this talk, I would like to focus more on what is sometimes called nanophotonics. So this includes nanoscale systems working at optical frequencies, and I will be focusing on systems that are possible, that can operate at room temperature. Okay, so the interest of this is that one can realize topological quantum nanophotonics, for instance, by interfacing with single emitters in the solid state. One can look at frequency conversion and other nonlinear effects due to the great enhancement of nonlinearities in nanoscale systems. And one can also look at lacing in this kind of systems. So in particular, I will look at sub-wavelength arrays of plasmonic nanoparticles, which show extremely confined light in the nanoscale working at optical frequencies. So can you see the pointer?
Yes.
Okay. Okay, because I removed the, okay, you see the mouse, that's fine, thanks. Yes, so along the same line, I will focus on systems that don't break the time reversal symmetry. So as you know, broadly speaking, there are two ways to arrive to a non-trivial topology. In one of them, one would break time reversal symmetry and look for physics similar or related to the quantum Hall effect, with purely unidirectional edge states that are non-reciprocal in photonic language. On the other hand, there is the possibility to look for systems that preserve the time reversal symmetry, but now we don't have the spin degree of freedom for photons. So the idea is to look for analogs of spin and realize spin polarized edge states that propagate in opposite directions. So in order to do this, one usually relies on spatial symmetries. And It can be done also using ring resonators by picking up different phases along different propagating directions in this kind of systems. So in particular, I will be speaking about some particularities of the nanophotonic system that I will consider, which is the long-range interactions. So when one has dipoles interacting among themselves, as you know, the interactions are not short range, as is the case, for instance, in coupled waveguide systems or coupled silicon resonators, which interact evanescently. But here, on the other hand, the interaction is long range and is affected by retardation. In fact, this generates interesting things like collective effects, so whereby the radiative properties of the dipoles can be greatly modified when one compares them to an isolated dipole, just purely because of this long-range interaction between them. And this has been exploited in several fields to realize metasurfaces, which can be made of plasmonic resonators, as I will be mainly discussing in this talk. But one can also realize the quantum version by using single emitters and exploit these same collective effects based on long-range interactions. So I will be discussing what is the particularities of these long-range interactions in some topological realizations in systems based on lattice symmetries. So I will start with a 1D chain, and then I will move on to dimensions. Okay, so firstly, the first thing that we considered was the SSH chain that we have already heard about this morning. So in my realization is similar to the one in the previous talk. So I consider an array, a 1D array of plasmonic nanoparticles whose size is much smaller than the wavelength. So they act basically as dipoles. And they are arranged with an alternating spacing. So this mimics the SSH model with 2 sublattices. So now, what are the differences between the usual SSH model and the model that I'm considering? First is the interaction range. So I don't have short interaction ranges as in a tight binding model. I have long range interactions, as I discussed. Next, I have retardation. So photons encode phase information. And also I have non-hermiticity because dipoles can couple to free space radiation, which is a continuum of modes. And I am not placing the dipoles within a cavity as the previous speaker was doing. So something that we can immediately see is that if we were to take a quasi-static and nearest neighbor approximation, this is an exact mapping to the SSH model where the edge modes are protected by chiral symmetry. And this is the reason for this, that there are only AB interactions. There are no interactions between particles in the same sublattice. However, these quasi-static and nearest neighbor approximations are only valid in very limited conditions. So firstly, they are only valid for the longitudinal electromagnetic modes in the chain. So these are modes whose polarization has the electric field aligned with the axis of the chain. It is only valid also for very sub-wavelength resonators. So in the case of the plasmonic nanoparticles, it would be very small nanoparticles with sizes much smaller than the wavelength, and also very sub-wavelength spacing between the particles. So we wanted to see what happened if we go beyond these approximations. And in order to do this, the first thing that we need to do is to find how to describe the particles. So we describe them using the polarizability. So this is very standard, but in case some of you may not be familiar with the specific of plasmonics, let me just mention a couple of details. So it is possible to describe the polarizability of a plasmonic nanoparticle in terms of the dielectric function, and this will show a resonance that is rather broad because the plasmonic nanoparticles are lossy. There is ohmic loss in the metal, and in the quasi-static limit, this is basically this kind of, the loss is basically given by this ohmic loss. But on the other hand, as soon as you increase a little bit the size of your plasma nanoparticle, you will also have radiative effects, which include the broadening. So we compare this quasi-static polarizability in red with this dashed line here, where the mode is quite broadened. And there are also important radiative shifts that shift the resonance quite a lot, and which is not plotted in this image. And then the next thing we have to do is to allow the dipoles to interact, to model the interaction between the dipoles. And for this, we use the coupled dipole model, which is also employed in many different situations when one has this type of problems of interacting dipoles. And the key points are that we include, we use the retarded Green's function to model the interaction between the dipoles. So this includes all interactions or long-range interactions between all the dipoles in a lattice. This includes all the modes. So there are longitudinal modes and there are transverse modes whose polarizations are along and transverse to the chain respectively. And one thing to note is that these transverse modes actually have have terms that are very slowly decaying. They decay as 1/r. Whereas in a quasi-static approximation, the modes decay as 1/r cubed. So with this, one builds a coupled dipole equation that relates the dipole moments of each of the lattice sides with the other dipoles through the Green's function and through the polarizability. And now for the infinite system, it's straightforward to write a Bloch eigenvalue equation, which is a generalized eigenvalue equation where the eigenvectors are the dipole moments and the eigenvalue is 1/the polarizability. And from here, we have access to the frequency, which is what most of the times we're interested in. And now how does this interaction matrix in this equation look like? It looks something like this. So the off-diagonal terms represent interactions between different sublattices, A to B, and this would be similar terms to the typical SSH model. And on the other hand, on diagonal, we have A to A couplings. And we will see the effect of this. Okay, so with this model, we calculate the band structure of some of these chains, and we start by considering chains with very small, very abundant nanoparticles and rather small periods. And we look at the transverse and longitudinal modes. And we see what is generally expected. So when we have the inversion symmetry, when we don't break inversion symmetry, so the particles are equispaced, we have a band closing, a gap closing. And by moving away from this point, we open the gap. And the full retarded calculation gives us bands that are qualitatively similar to the bands that one would calculate in the quasi-static regime. One thing to notice is that our bands are not symmetric around the resonance frequency of the dipoles, which would be this surface plasmon frequency here. And this is because we include interactions between all the particles, which already breaks the chiral symmetry, so we lose the symmetry in the bands. But then if we move beyond and increase the periodicities and the size of the particles, we start to see things that greatly differ from the expected tight binding picture. So we start to see how the bands close, the gap closes where one was not expecting, and it behaves very differently for transverse and longitudinal modes. And so we see two examples here where the gap is closed for transverse and open for longitudinal modes, and the opposite for different parameters. Okay, so what is happening here? The first thing to realize is that we actually have a non-Hermitian model. So we should actually be plotting, before I was plotting a projection of real frequencies in the real frequency plane, but we should be looking at these bands in the complex frequency. And when we do this for the longitudinal modes of, in this case, of these parameters, we see that the bands, there are two bands that are actually separated in complex space, so the gap is not closing. And when we calculate for a finite chain in the topological phase, so where the subphase is phi, we do find the two edge modes here. Also, I should point out that here we have generalized our calculation to the of the SAC phase to the non-Hermitian version, where to be able to account for this complex frequency property. And then the next thing to realize here is that we have a way to break chiral symmetry that is quite curious. So I have already said that these long-range interactions necessarily break chiral symmetry, and this has also been discussed this morning. But the point is that for these longitudinal modes, we still find the edge modes located at the middle of the gap in this non-Hermitian scenario. And the thing is that there is the way we break chiral symmetry is quite curious because it is done by adding matrix elements to the diagonal of the interaction matrix. And because the SAC phase depends only on the eigenvectors, even if the eigenvalues are changing, the eigenvectors of the full non-Hermitian system are the same as the eigenvector of a chirally symmetric system. So this gives us the same SAC phase. And as one would expect for the chirally symmetric system, where this where this A to A lattice hoppings would not appear, and one can still find the edge modes. And as a result, we also we see that if we look at these edge modes, they are predominantly sitting on one sublattice, although there is some excitation of the other sublattice, which would be absent if we were respecting the chiral symmetry. Now, this was for longitudinal modes, but on the other hand, there is a very important effect on transverse modes. So these transverse modes are the ones that have the longer decay rate with 1/r. And in this case, chiral symmetry is actually very strongly broken when we increase the periodicity. And even if we could calculate this non-Hermitian version of the SAC phase, this strong breaking of chiral symmetry makes us lose the edge modes in these cases. Okay, so with this, I have discussed some of the effects of long-range interactions in topology for 1D systems. So let me move on to two-dimensional lattices. So the system that we started studying was this breeding honeycomb lattice that has been introduced briefly by one of the speakers in this session. And but I would like to point something. So it was proposed as a phase to mimic the quantum spin Hall phase based only on lattice symmetries in a photonic crystal. And originally it was interpreted as a set2 topological phase because apparently it hosts two pseudospins that propagate in opposite directions along the edge. So this has been realized in many experimental setups. We have seen one example also in the previous talk, in the other talk in this session. So let me show you what we did with these kind of dipolar nanoparticles. So the Hall effect is based on a band inversion. And here I show it for our system, which in this case consists of elongated nanoparticles, and I am considering the out-of-plane modes. So there is a phase transition between a system where these 6 elements in the hexagonal unit cell are contracted and when they are expanded. So when they are contracted, we see that and the ordering of the modes is the one that one would expect. So monopolar, dipolar, quadrupolar, etc. modes. And when the system is in the expanded phase, the ordering of the modes close to this band gap opening is flipped. Okay, and this can be seen in our plasmonic metasurface system. This is something that can be probed in the far field by because while the dipolar modes would couple to an incident plane waves, the quadrupolar modes won't. So this is possible to be detected as a shift in the extinction cross section of this system. So next we look at the edge modes, and the first thing we notice when we look at a ribbon, at a finite system, is that the edge modes are gapped. And in fact, for our system and our parameters, the gap is quite large compared to the full band gap, and also they do not connect to the bands. So we were for some time trying to understand this and its relation to the quantum spin Hall effect, where you know that topological edge modes should cross in a Dirac crossing, and they should join the bulk modes. On the other hand, if we look at the edge modes in propagating in opposite directions, we do find that they have a pointing flux that propagates in opposite directions. But furthermore, we looked at the electromagnetic spin. So this is the degree of chirality, or the degree of circular polarization. In this case, it corresponds to the magnetic field. And as you can see, it has opposite signs for the oppositely propagating modes. And this represents that the handedness of the circular polarization in the plane is opposite for the two oppositely propagating modes. So now we can use this to test the source directionality by using circularly polarized magnetic dipoles. So we choose a dipole of a given handedness, and we place it at different positions in the unit cell. And what we find is that when we place it close to the center of the unit cell, a mode that propagates toward the right is excited, but then we move it a bit closer to the interface, and a mode propagating in the other direction is excited. And this can be directly related to the handedness of the edge mode given by the spin quantity that I showed you before. So we can also define some beta factors of coupling to the right or the left propagating edge modes, and do this kind of contour plots where we test many dipole sources positions, and we find that there is a larger coupling to the right propagating mode when the emitter is placed close to the unit cell center. And on the other hand, when it is placed at the interface, the coupling to the left propagating mode is larger. So it is important to consider the emitter positions to actually understand any directionality that is observed in any of these experiments. And this is very related to what the previous speaker in this session did for the Valley Hall lattice. So this is something that we pointed out and that is not generally considered when speaking about this lattice. And for this reason, we think that this is not a great and exact analog of a quantum spin Hall. So in essence, in the original paper, the quantum spin Hall phase was justified by describing a pseudo-time reversal symmetry that is related to the lattice symmetries. But the truth is that it has been shown that this time reversal operator is actually not a global symmetry of the system because of the inequivalence between the k and k prime points. So it is only valid at gamma, basically, and this relates to the reason why we see the edge mode of the appropriate direction propagation excited when we place our emitter close to the unit cell, the center of the unit cell. So in fact, there wasn't a proper first principle calculation of the topological invariant of this topological phase before this calculation by the team of Dario Versugo and Itzol Garcia-Echarri from DIPC, who calculated the Wilson loops for this kind of structures. And here I'm showing our calculation the Wilson loops for our plasmonic realization, and where we see the same conclusions. And the main point, the key point here is that the Wilson loop is not winding, so it's not accumulating a phase as we travel from the center of from one unit itself to the next one. Whereas in contrast, in the expanded phase, what it's doing is it is what is called usually in an obstructed limit. So this means that the Vanier centers are localized not at the center of the unit cell, but at the edges, and this gives rise to physics that is reminiscent of the SSH model. So we have edge modes and so on, but in our opinion, it's not really a spin-hole phase. So finally, we look at also at the retardation effect. So we look at what happens for larger periods with the edge modes, as I was doing for the one-dimensional case. And I plot the extinction cross-section of the modes here at normal incidence as I increase the lattice period. And what can be seen is that at some point, that's for some values of the period, everything is lost by radiative broadening and shiftings of the bulk bands, and so we basically lose the physics of the epistate. So a bit less in the SSH model, if one wants to realize these topological phases with dipoles only, it is necessary to work with shorter periods. Okay, so then in a couple of minutes, let me just go to the last part of the talk. So the next thing that we did was we moved to study topological cavities. So now instead of an infinite edge, we consider a closed cavity. And we started doing this, we first did it for a photonic crystal with the same breathing honeycomb symmetry that, that I discussed. And what we found was that the edge modes are quantized within the bandgap, and they appear in pairs of the generated states with the opposite circular polarization. And this is very related to what was discussed in the talk by the Sheffield groups, where they observed this kind of edge states between so this kind of quantized, standing waves in a resonator states within the bandgap. And next, we moved on to study corner modes. And our interest here was mainly to see also the effect of long-range interactions. So we implemented a model where we have dipolar resonators again of the breathing in the breathing honeycomb lattice. Inside this hexagon, they are in one phase. Outside the hexagon, they are in the other phase. And we artificially tune the interaction range between the dipoles. So we include this cutoff so that the interaction range moves from pure linear neighbor here to the full long-range interactions. And what we see is that basically increasing the interaction range breaks the chiral symmetry as expected, so it breaks the chiral symmetry of the spectrum. And while we were starting with 6 purely degenerate corner modes of the 6 symmetries I enabled by the lattice, the 6 corner modes start to shift a little bit away from zero energy, and they also their degeneracy splits up. However, we find numerically that even though we're breaking the chiral symmetry, these corner modes can still be found there when we include random disorder in our calculations. And we attribute this to the system being reducible to a chiral symmetric limit when the interactions are very short range. And additionally, there is this fact that is quite specific of this lattice, that is that we can remove some particles in the that lie along the edge, the cavity edge, and the corner states are not affected at all. And the reason for this is that is the underlying chiral symmetry that is not broken strongly enough in this system. So just a final comment about the breathing Kagome lattice. We did also a similar study as with the breathing honeycomb lattice. And I will just mention that we studied similarly the effect of disorder in this kind of cavities and its effect on the corner modes in this kind of cavities. And what we found was that while a retardation breaks chiral symmetry and it imposes some limitations, at the same time, it also allows for the existence of modes that are delocalized along around the whole cavities in the perfectly non-disordered situation. And the retardation is needed for this, and this would be interesting to generate, for instance, long-range interactions between emitters that could be placed at different corners. So with this, I just thank all the people involved in this work, and mainly Matthew Proctor, who was recently finished his PhD, and also the team at the IPC, Maria Blanco de Paz, Dario and Aitzol, and previous collaborators from Imperial College. And I leave this advertisement here. Thank you.
Okay, thank you, Paloma. It's a very nice talk. Thank you for the announcement as well. Let me see. Are there any questions? So you can either raise your hand or write them on the chat, please. I hope people are not going for lunch already. For Spain, it's pretty early, so maybe somewhere else it's not so much.
I will start.
Alex?
So not even in the expanded limit of the honeycomb, you would consider this kind of a topological kind of a structure, or?
So I'm not saying that it's not topological. What I'm saying is that it is not an exact analog of a quantum spin Hall size, which is what people usually say. And the main, for me, one obvious thing is that the edge modes are gapped, and you need to choose carefully where you put your emitter. So the physics here is a bit like in between topological protection and the typical chiral coupling in photonic crystals that was studied a lot a few years ago.
So because in your case, this thing that you were emphasizing a lot about, the thing that the emitter position plays or a big role. So you somehow, if it was a real analog, then it shouldn't matter that much. This is what you mean, like.
Yes. So so maybe the point with the analog here is that what this means is that there is a spin mixing, no? So it is difficult to couple purely to a mode that propagates only to the right or only to the left. That's what one would expect really with a quantum Hall effect, quantum spin Hall effect protected by the time reversal symmetry. So you would expect these situations, no? So, and also something interesting is that if we take this kind of calculations where we studied the optimal positions to couple to one or the other propagation, and if we average these beta factors that we obtain here, it averages basically very close to zero. So then in order to understand experimental results, one has to do something like it was shown for the Valley Hall system in the other talk. One needs to specify where is your emitter, or I guess, yes, the samples are created and then and they look for places where the emitter is actually in a good position. And this is not always discussed in the experimental literature. So this is the point I wanted to make.
Okay, thanks.
Thanks.
I have, to be honest, I would have quite a few questions, but we don't have so much time. I would like at least ask you about when you say that your system is reducible to a chiral symmetric limit. I was a bit curious, what do you mean by that? Because I understand you mean that somehow, even though chiral symmetry is broken because of long-range interactions, still the usual topological description for chiral systems applies somehow? Can you?
Yes, so what I mean here is that with the long range interactions, I'm definitely breaking this chiral symmetry, but I can make a continuous deformation to a system that is chirally symmetric. So then, as long as this, as long as I don't break the symmetry strong enough, so for instance, as long as I don't close the bulk gap and so on, I can still observe pretty much the same physics.
Okay.
Is what I mean.
So you can observe that
this kind of corner modes have been observed in experiments in similar. So they have been observed in photonic crystals, but also in evanescent waveguides and so on. But also with nanoresonators like dielectric nanoparticles and these kind of things, where this kind of physics, where this physics would be relevant, and they still observe the edge modes. So we wanted to find an explanation, no, to see even if we are breaking these long-range interactions, what is going on.
I see. Yeah, that's very interesting. So Maria Blanco is asking something. Let me see if I can unmute her. Yes, Maria, you can.
Hi, yes, I'm here. Super nice talk, Paloma. I was thinking that if there's any property of the quantum Hall effect state that is interesting, and the other states of due to the chiral symmetry doesn't have. I mean, it's worth it to look for.
So if it's worth, you mean if it's worth realizing a real analog of the quantum Hall effect?
Yes, that is the question. Thank you.
Yes. So I think so. I think it's worth it, and there have been examples in the literature already. And the main thing is that they observe. So for the quantum Hall effect, you get purely non-reciprocal edge modes, and that's very interesting because you can use that to mediate interactions that are purely non-reciprocal and so on. But yes, our point was trying not to break the reversal symmetry, because in general for these nanoscale setups it's difficult. But there are of course other systems where you can go that route, and that's very interesting.
Okay,
thanks, Maria.
Okay, thank you, Paloma, and thank you to all the speakers in this session. And so we have a break until 2:30, I think. And see you later then. Bye. Thank you.
See you later. Thanks.
Bye.